Welcome to the ultimate guide to quantum gravity, the quest to understand the very fabric of our universe. For decades, physicists have been working tirelessly to reconcile the two great pillars of modern science, general relativity and quantum mechanics. General relativity explains the large-scale structure of the universe, describing gravity as the warping of space-time by mass and energy. Quantum mechanics, on the other hand, governs the microscopic world of particles, waves, and probabilities, where uncertainty reigns supreme. These two theories are astonishingly accurate in their respective domains, yet they fail to agree when brought together at the smallest scales. At the heart of this conflict lies the challenge of describing gravity in the quantum realm, where space-time itself becomes uncertain and fragmented. Quantum gravity seeks to resolve this, providing a unified framework that explains all forces and particles in the universe. In this video, we'll explore the fascinating approaches that scientists have developed to tackle this mystery, from string theory to loop quantum gravity. We'll dive into the implications for black holes, the early universe, and the nature of reality itself. Join us as we embark on a journey through the frontiers of physics, uncovering the secrets of quantum gravity. Einstein's field equations form the backbone of general relativity, describing how matter and energy influence space-time. These equations reveal that gravity isn't a force acting at a distance, but a result of space-time curvature. At their core, these equations connect the geometry of space-time to the energy and momentum within it. They show that massive objects like stars and planets distort space-time, creating what we experience as gravity. Each term in Einstein's field equations carries deep physical meaning, linking abstract mathematics to observable phenomena. The curvature of space-time is represented by tensors, intricate mathematical objects describing its shape. Energy and momentum, encoded in the stress-energy tensor, dictate how space-time bends. This dynamic interplay creates the cosmic dance of galaxies, stars, and planets. Solving these equations isn't straightforward, often requiring approximations or numerical techniques. Despite their complexity, they've been tested with remarkable precision in countless experiments. One of the first major successes of Einstein's equations was explaining Mercury's orbit. Its slight deviation, unexplained by Newtonian gravity, became clear through general relativity. Another triumph came with the prediction of gravitational waves, ripples in space-time caused by massive objects accelerating. These waves were directly observed for the first time in 2015, a century after Einstein's prediction. Black holes, enigmatic cosmic objects, also emerged naturally from solutions to these equations. Their existence challenges our understanding of space, time, and the limits of physics. Einstein's field equations also play a key role in describing the evolution of the universe. They underpin the Big Bang theory, explaining the expansion of space-time itself. Cosmologists use these equations to study phenomena like dark energy and the fate of the cosmos. Despite their age, Einstein's insights continue to shape modern physics. While incredibly powerful, the equations break down at quantum scales, where space-time loses its classical smoothness. This limitation is one of the driving forces behind the search for quantum gravity. By examining these equations, we gain a profound understanding of the universe's structure and the forces that shape it. They remain a cornerstone of our quest to unify the laws of nature. Space-time curvature is at the heart of Einstein's vision of gravity. Rather than being a force pulling objects together, gravity emerges from the bending of space-time caused by mass and energy. This curvature is what guides the motion of planets, stars, and even light itself. Objects follow paths within the curved fabric of space-time, creating the illusion of gravitational attraction. The simplest way to picture this is to imagine a stretched rubber sheet. Place a heavy object in the center, and the sheet dips, just as space-time curves around a massive object. Smaller objects placed near the dip naturally move along the curves, mimicking gravitational behavior. Though simplistic, this analogy captures the essence of how gravity works in Einstein's theory. A prime example of space-time curvature in action is gravitational lensing. Light from distant stars bends as it passes near massive objects, producing stunning arcs and halos in the sky. This effect not only confirms the warping of space-time, but also allows astronomers to study distant galaxies and uncover hidden dark matter. The curvature of space-time, in this sense, becomes a tool for exploring the cosmos. Spacetime curvature isn't just limited to massive celestial bodies. Even small objects warp the fabric of spacetime, though the effect is imperceptible at human scales. For larger masses, like black holes, the curvature becomes extreme. Near a black hole, spacetime bends so sharply that not even light can escape its grasp, creating a region of no return. Einstein's equations describe this curvature mathematically, offering precise predictions about how objects move in the presence of gravity. These predictions align perfectly with observed phenomena, from planetary orbits to the bending of starlight. However, this smooth, continuous model of spacetime breaks down when examined at the quantum level. At tiny scales, the geometry of spacetime is thought to become fragmented, hinting at the need for a quantum theory of gravity. Even so, the concept of spacetime curvature remains one of the most elegant and accurate descriptions of gravity ever devised. It transforms our understanding of the universe, shifting gravity from a force to a geometric consequence. From the movements of galaxies to the behavior of light, spacetime curvature defines the structure and dynamics of the cosmos. Its study continues to illuminate the profound relationship between matter, energy, and the universe itself. Key experimental evidence has solidified general relativity and spacetime curvature as cornerstones of modern physics. These observations have repeatedly validated Einstein's predictions with astonishing precision. One of the earliest confirmations came during a solar eclipse in 1919. Light from distant stars was observed bending around the sun, directly demonstrating the warping of spacetime. This phenomenon, known as gravitational lensing, has since become a powerful tool for astronomers. It allows us to map dark matter and study galaxies far beyond the reach of traditional telescopes. The orbit of Mercury provided another key piece of evidence. Its slight deviation from Newtonian predictions was perfectly explained by Einstein's equations, a triumph for general relativity. Gravitational redshift, where light changes frequency as it escapes a gravitational field, offers further proof. This effect has been observed in experiments on Earth and in light from distant stars. Modern GPS systems also provide indirect evidence of space-time curvature. These satellites account for general relativity to maintain their accuracy, highlighting the theory's relevance in daily life. Gravitational waves, ripples in space-time caused by massive objects accelerating, marked another milestone. Their direct detection in 2015 confirmed a prediction Einstein made a century earlier. These waves, observed from colliding black holes and neutron stars, have opened a new window into the universe. They allow us to study violent cosmic events in ways that were previously impossible. Time dilation near massive objects has been observed and measured with precision. Atomic clocks placed at different altitudes demonstrate that time passes slower closer to Earth's surface. The expansion of the universe, first observed through redshifted light from galaxies, ties directly to Einstein's equations. These observations support the idea of space-time itself stretching over time. The cosmic microwave background, a relic of the early universe, offers insights into the large-scale curvature of space-time. Its precise patterns align with predictions from general relativity. Each of these experiments and observations not only supports the theory, but also reveals the vast interconnectedness of the universe. They serve as stepping stones in our journey toward deeper understanding. General relativity, while remarkably successful, encounters significant challenges at quantum scales. At these extremes, the smooth fabric of spacetime described by Einstein begins to unravel. The Planck scale, where quantum effects dominate, reveals a realm where spacetime is thought to become highly chaotic and fragmented. Here, the concepts of curvature and continuity no longer apply in their classical sense. Singularities, such as those found at the centers of black holes, push general relativity beyond its limits. At these points, the equations break down, offering no clear description of the physics involved. Another key issue is the incompatibility with quantum mechanics. While general relativity governs the large-scale structure of the universe, it fails to incorporate the probabilistic nature of the quantum world. In quantum mechanics, particles behave as waves, existing in superpositions of states. Attempting to apply this framework to spacetime introduces contradictions that general relativity cannot resolve. The uncertainty principle, a cornerstone of quantum theory, conflicts with the deterministic nature of spacetime geometry. This tension highlights the need for a unified description that works at all scales. Efforts to quantize gravity by treating spacetime itself as a quantum field have faced significant roadblocks. The resulting theories often produce infinities that cannot be reconciled mathematically. Another limitation arises in describing interactions involving extreme energy densities. At these scales, neither general relativity nor quantum mechanics alone provides accurate predictions. Experiments have yet to directly probe quantum gravity phenomena, leaving much of this frontier as theoretical speculation. The inability to test predictions in this regime complicates the development of a comprehensive theory. Despite these challenges, hints of quantum gravity effects may appear in specific scenarios, such as near black holes or during the early moments of the universe. These contexts offer tantalizing opportunities to bridge the gap. The limitations of general relativity at quantum scales also inspire exploration into alternative frameworks. Concepts like spacetime discreteness or extra dimensions arise as potential solutions to these deep issues. Ultimately, understanding the quantum nature of spacetime is essential for answering some of the most profound questions in physics. These limitations drive the ongoing search for a theory that unites the forces of the universe. The relationship between spacetime and the cosmos lies at the core of our understanding of the universe. General relativity provides the foundation for studying the large-scale structure and evolution of everything we see. Spacetime acts as the stage upon which the cosmic drama unfolds, dictating how galaxies, stars, and planets move and interact. It is both a framework and a dynamic entity, shaped by the distribution of matter and energy. The expansion of the universe itself is a manifestation of spacetime's properties. Einstein's equations describe how spacetime stretches, creating the observed redshift in light from distant galaxies. Dark energy, a mysterious force driving the accelerated expansion of the universe, is deeply tied to the structure of spacetime. Its nature remains one of the most significant puzzles in cosmology. Cosmic phenomena, such as black holes and neutron stars, provide unique environments where the relationship between spacetime and matter becomes most extreme. These objects reveal the intricate ways in which spacetime responds to gravity at its most intense. Even the formation of galaxies is influenced by the curvature of spacetime. The way matter clusters on large scales is determined by gravitational interactions shaped by spacetime's geometry. The early universe, moments after the Big Bang, offers critical insights into spacetime's nature. During this period, quantum effects and spacetime dynamics work together to shape the cosmos as we know it. The cosmic microwave background is a snapshot of spacetime from billions of years ago. Its patterns encode the geometry of the universe and provide evidence for the interplay between matter and spacetime over cosmic time. Gravitational waves ripple through the fabric of spacetime, carrying information about the most violent events in the cosmos. Their detection has revolutionized our ability to study distant and otherwise invisible phenomena. Even time itself is a function of spacetime, varying depending on the presence of gravity. This relativity of time connects the vast scales of the universe to the experiences of individuals on Earth. The cosmos continually shapes spacetime, just as spacetime shapes the cosmos. This interconnected relationship is key to understanding both the past and future of the universe. By studying this profound connection, physicists aim to unlock deeper truths about the nature of existence, from the behavior of galaxies to the ultimate fate of spacetime itself. Quantum theory revolutionized our understanding of the universe by revealing the strange behavior of matter and energy at the smallest scales. It challenges classical ideas, replacing certainty with probability and fixed paths with a realm of possibilities. At its core is the wave-particle duality, where particles like electrons and photons can behave as both particles and waves, depending on how they're observed. This duality blurs the boundaries between categories once thought distinct. Superposition, another fundamental principle, states that particles can exist in multiple states simultaneously until measured. It's this principle that powers technologies like quantum computing and challenges our intuition about reality. Entanglement, often described as spooky action at a distance, shows that particles can be connected in ways that make their states interdependent, no matter the distance between them. This phenomenon has profound implications for communication and information security. The uncertainty principle reveals a fundamental limit to what can be known about a particle's position and momentum simultaneously. This limitation isn't due to experimental error, but is intrinsic to the nature of reality. In quantum mechanics, the act of observation plays a crucial role. Measuring a system causes its wave function to collapse, forcing the particle into a definite state and raising questions about the role of the observer. The mathematical framework of quantum theory relies on wave functions, which describe the probabilities of where particles might be found. These probabilities form the backbone of quantum predictions. Quantum fields extend these ideas, treating particles as excitations in underlying fields. This perspective allows quantum theory to describe interactions between particles with incredible precision. Energy quantization, where particles can only occupy specific energy levels, explains phenomena like the stability of atoms and the emission of light in discrete packets called photons. Quantum tunneling showcases the non-intuitive behavior of particles, allowing them to pass through barriers they seemingly shouldn't be able to cross. This principle underlies technologies like semiconductors and fusion. The quantum world defies classical determinism, where outcomes are predictable given initial conditions. Instead, it introduces probabilistic laws that govern the behavior of matter and energy at the smallest scales. Though bizarre, these core principles of quantum theory form the foundation of modern physics, leading to groundbreaking advancements in technology and reshaping our understanding of the universe. Quantum states describe the complete information about a particle, encompassing all the probabilities of its possible outcomes. These states are represented mathematically by wave functions, which capture the full complexity of quantum systems. Superposition is one of the most fascinating aspects of quantum states, where particles can exist in multiple configurations at once. Until measured, these overlapping possibilities coexist, defying classical intuition. This phenomenon can be illustrated with Schrödinger's famous thought experiment, where a cat in a box is both alive and dead until observed. While a metaphor, it highlights the peculiar nature of quantum superposition. Superposition isn't confined to theoretical ideas, it has real-world applications, such as in quantum computing. Quantum bits, or qubits, leverage this principle to perform calculations far beyond the reach of classical computers. When a quantum state is measured, superposition collapses into a single outcome. This collapse is fundamental to the unpredictability of quantum mechanics and the limits of observation. Quantum states are not static. They evolve according to the Schrödinger equation, which governs how probabilities shift over time. This dynamic nature allows for phenomena like interference patterns in experiments. Entanglement is deeply connected to superposition, as the states of entangled particles rely on shared probabilities. When one particle is measured, the state of its partner collapses instantly, no matter the distance. The principle of superposition challenges the classical idea of a well-defined reality. Instead, quantum mechanics suggests that reality is a tapestry of probabilities that solidify only through interaction or measurement. In double-slit experiments, particles passing through both slits simultaneously create interference patterns, a striking demonstration of superposition. The results vanish when observation forces the particles to choose a path. Superposition has profound implications for understanding information in the quantum realm. The ability to encode multiple possibilities simultaneously is key to developing revolutionary technologies. Despite its strange implications, superposition is one of the best-tested principles in science. Experiments consistently validate its predictions, underscoring the reliability of quantum mechanics. Quantum states and superposition reveal a universe far stranger and more intricate than classical physics could have imagined, opening doors to new discoveries and possibilities. Uncertainty lies at the heart of quantum mechanics, challenging the classical notion of predictability. It establishes that certain pairs of properties, like position and momentum, cannot both be known precisely at the same time. This is not due to limitations in measurement, but reflects a fundamental property of nature itself. The Heisenberg uncertainty principle encapsulates this concept, setting a limit to what can be simultaneously determined. Wave-particle duality further complicates our understanding of quantum systems. Particles like electrons and photons exhibit characteristics of both particles and waves, depending on how they are observed. This duality is beautifully demonstrated in the double-slit experiment. When unobserved, Particles form interference patterns typical of waves. When observed, they behave as individual particles. The wave aspect of particles is described by their wave function, a mathematical representation of all possible states. This wave-like nature governs how particles propagate and interact. At the same time, the particle-like behavior is evident in phenomena like the photoelectric effect, where photons transfer energy in discrete packets. This dual nature underpins much of quantum theory's success. Uncertainty and wave-particle duality work together to define the probabilistic behavior of quantum systems. These principles explain why we can predict likelihoods but not definite outcomes. This probabilistic framework challenges classical determinism, where outcomes are fully determined by initial conditions. Instead, quantum mechanics introduces an inherent randomness to the universe. Wave-particle duality also plays a crucial role in quantum technology. Devices like electron microscopes and lasers exploit these dual behaviors to achieve precision and innovation. Uncertainty shapes how particles interact and form bonds, influencing the very fabric of matter. It provides insight into why atoms have specific structures and why energy levels are quantized. The dual nature of particles is not merely a curiosity, but a core feature of the physical world. It helps explain phenomena that classical physics could not, like the behavior of light and the stability of atoms. Together, uncertainty and wave-particle duality reveal a universe that operates on principles far removed from everyday experience, offering profound insights into the nature of reality. Quantum field theory forms the foundation of modern physics, combining quantum mechanics with special relativity. It describes particles not as isolated objects, but as excitations in underlying fields that permeate the universe. Each type of particle corresponds to a specific quantum field. For example, electrons arise from the electron field, while photons emerge from the electromagnetic field. These fields are dynamic, existing everywhere in space and time. Even in a vacuum, they fluctuate constantly, creating a restless and unpredictable quantum landscape. Interactions between particles occur through the exchange of force carriers, known as gauge bosons. These exchanges are mediated by fields and define the fundamental forces of nature. Quantum field theory successfully explains electromagnetism, the weak force, and the strong force through a framework called the Standard Model. Gravity, however, remains a challenge to fully incorporate. The mathematical formalism of quantum field theory uses operators and commutators to describe how fields evolve and interact. These tools allow precise predictions of particle behavior in various contexts. Renormalization is a key technique in the theory, addressing infinities that arise during calculations. By redefining parameters like mass and charge, physicists obtain finite and meaningful results. Virtual particles, another feature of quantum fields, appear briefly in calculations to mediate forces. Though fleeting, they play a critical role in explaining how particles interact at a distance. Feynman diagrams provide a visual representation of particle interactions in quantum field theory. These diagrams simplify complex equations and offer insight into the mechanics of collisions and decays. One of the triumphs of quantum field theory is quantum electrodynamics, which describes how light and matter interact. Its predictions have been confirmed with unmatched precision in experiments. The theory also predicts phenomena like particle-antiparticle pair creation, where energy transforms into matter. This process demonstrates the deep connection between quantum fields and the fabric of reality. Quantum field theory continues to evolve, providing a framework to explore new physics beyond the Standard Model. It is essential for understanding the universe at both the smallest and largest scales. Quantum mechanics, while profoundly accurate, has its own set of limitations when describing the universe. It provides precise predictions for small-scale systems, but struggles when applied to gravity and spacetime. One major limitation is its inability to address phenomena at extremely high energies or tiny scales, such as near singularities or during the early moments of the universe. In these cases, the framework of quantum mechanics breaks down. Another challenge arises in unifying quantum mechanics with general relativity. While quantum mechanics excels in describing particles and forces, it cannot explain the fabric of spacetime itself. The deterministic nature of general relativity conflicts with the probabilistic foundation of quantum mechanics. This tension highlights the need for a more comprehensive theory, like quantum gravity. Quantum mechanics also does not inherently explain dark matter or dark energy, which comprise most of the universe. These mysterious components remain outside its scope. The theory relies heavily on the observer effect, where measurement influences the system being studied. This raises philosophical questions about the role of observation in defining reality. In systems involving large numbers of particles, quantum mechanics becomes impractical. Classical physics often emerges as an approximation, but the exact process of this transition remains unclear. Decoherence is another limitation, where quantum superpositions appear to collapse due to interactions with the environment. While it helps explain the classical world, it doesn't fully resolve the measurement problem. The inability to directly observe quantum phenomena at scales relevant to quantum gravity makes experimental verification difficult. Without experimental data, many theoretical extensions remain speculative. Quantum mechanics assumes a fixed spacetime backdrop, which general relativity contradicts. This fundamental disconnect prevents a unified description of nature's forces. Another limitation is in handling non-locality, such as the behavior of entangled particles. While predictions are accurate, the deeper explanation for these phenomena remains unresolved. Despite its incredible success, quantum mechanics is not the ultimate framework. Its limits drive the search for a more complete theory that can unify all aspects of the physical universe. Relativity and quantum mechanics conflict because they are built on fundamentally different principles that describe the universe in incompatible ways. General relativity views spacetime as a smooth, continuous fabric, while quantum mechanics reveals a discrete and probabilistic nature at the smallest scales. At large scales, relativity treats gravity as the curvature of spacetime, providing a deterministic framework for the motion of planets and galaxies. Quantum mechanics, however, describes particles and forces using probabilities and wave functions, where outcomes are inherently uncertain. This divide becomes evident at the Planck scale, where both quantum effects and gravitational forces are equally significant. In this realm, the smooth spacetime of relativity clashes with the fragmented and fluctuating nature of quantum fields. Relativity requires spacetime to be continuous and differentiable, ensuring that curvature is well defined. Quantum mechanics, on the other hand, introduces fluctuations that make spacetime appear chaotic and unpredictable at tiny scales. Another source of conflict lies in how the two theories treat time. In relativity, time is a flexible dimension that can stretch and contract depending on gravity and motion. Quantum mechanics, however, assumes a fixed and universal time for calculating probabilities. Relativity's geometric description of gravity as spacetime curvature is incompatible with the force-based interactions of quantum mechanics. Quantum particles exchange discrete quanta of energy, while relativity describes energy as part of a continuous field. Attempts to apply quantum mechanics to spacetime often result in infinities that cannot be resolved. These mathematical divergences signal a fundamental mismatch between the two frameworks. The conflict is particularly stark near singularities, such as those at the centers of black holes or during the Big Bang. Here, the infinite densities predicted by relativity cannot be reconciled with the quantum nature of particles and fields. Quantum mechanics depends on a static spacetime backdrop, while relativity requires that spacetime itself be dynamic and influenced by matter and energy. This fundamental difference prevents a unified description of the universe. Even concepts like locality differ between the two theories. Relativity upholds that information cannot travel faster than light, whereas quantum entanglement suggests instantaneous connections across vast distances. The lack of experimental access to scales where both theories apply simultaneously exacerbates the problem. Without direct observations, bridging the gap between these frameworks remains a daunting theoretical challenge. This profound conflict underscores the need for a new theory, such as quantum gravity, that can seamlessly integrate the principles of both relativity and quantum mechanics into a unified framework. Singularities are regions where the laws of physics as we know them cease to function. They represent points of infinite density and curvature, where space-time becomes so warped that our current theories break down. One of the most well-known examples of a singularity is found at the center of a black hole. Here, the gravitational pull is so intense that not even light can escape, and the core collapses into a point of infinite density. Singularities also appear in the theoretical framework of the Big Bang. At the moment of the universe's creation, spacetime is thought to have been compressed into a singularity before expanding rapidly in all directions. General relativity predicts these singularities, but it cannot describe what happens within them. The infinite values they produce in equations suggest the need for a new theory to explain their nature. Quantum mechanics also struggles with singularities. It provides no clear way to handle the extreme conditions where particles and spacetime are compressed to unimaginable scales. Horizon surfaces, like the event horizon of a black hole, hide singularities from direct observation. This boundary marks the point where the escape velocity exceeds the speed of light, sealing off the singularity from the rest of the universe. Some physicists propose that singularities might not truly exist. Instead, they may be artifacts of the limitations of general relativity, with quantum gravity offering a smoother resolution at these extremes. Understanding singularities requires reconciling the macroscopic predictions of relativity with the microscopic behavior of quantum particles. This interplay between large and small scales remains one of the greatest challenges in modern physics. The information paradox tied to black hole singularities poses another puzzle. It questions how information about particles falling into a black hole might be preserved or lost, conflicting with quantum mechanics. Cosmic censorship conjectures aim to explain why singularities remain hidden within black holes and do not appear in observable regions of the universe. These ideas suggest nature might shield us from their disruptive effects. Singularities are not just theoretical curiosities. They hold the key to understanding the origins of the universe and the ultimate fate of matter under extreme conditions. They bridge the gap between cosmology and particle physics. Exploring these enigmatic points could unlock new laws of physics, offering insights into the structure of spacetime and the fundamental forces that govern the cosmos. The Planck scale represents the realm where both quantum mechanics and general relativity converge, and where their limitations become most apparent. At this minuscule scale, around 10 to the negative 35th meters, the fabric of spacetime is theorized to break down into a chaotic and granular structure. Phenomena at the Planck scale defy classical descriptions, as the smooth spacetime of relativity gives way to fluctuations dominated by quantum effects. Energy densities reach such extremes that traditional concepts like distance and time lose their conventional meanings. Planck units, such as Planck length, time, and energy, provide a natural framework for discussing these scales. They are derived from fundamental constants, including the speed of light, Planck's constant, and the gravitational constant. At this scale, quantum foam is thought to dominate, with spacetime itself behaving unpredictably, bubbling with virtual particles and fluctuating geometries. This chaotic behavior suggests that spacetime might not be continuous, but instead made up of discrete units. Black holes that reach the Planck scale are known as Planck scale black holes. These hypothetical objects could serve as laboratories for studying quantum gravity, revealing the interactions of spacetime and matter at their most fundamental level. String theory offers one potential way to understand Planck scale phenomena by proposing that particles are not points but tiny vibrating strings. These strings could replace singularities with finite, well-defined structures. Another approach comes from loop quantum gravity, which suggests that spacetime is quantized into tiny loops, avoiding the infinities predicted by general relativity. This theory envisions spacetime as a dynamic network of discrete connections. Planck-scale phenomena also play a crucial role in understanding the early universe. Moments after the Big Bang, the universe existed in a state where these extreme conditions governed its behavior, shaping the cosmos we observe today. The concept of extra dimensions proposed by some theories may become significant at the Planck scale. These additional dimensions could influence particle interactions and the structure of spacetime itself. Experimental evidence for Planck-scale phenomena remains elusive due to the immense energies required to probe such tiny scales. However, indirect observations, such as deviations in high-energy cosmic rays, might offer clues. Studying the Planck scale is essential for resolving the conflict between quantum mechanics and relativity. It holds the key to understanding phenomena like singularities, black hole interiors, and the origins of the universe. Ultimately, the Planck scale represents the frontier of theoretical physics, offering a glimpse into the deepest layers of reality and the fundamental workings of the universe. At the quantum level, energy and gravity interact in ways that challenge our understanding of physics. Gravity, which dominates at large scales, appears weak compared to the other fundamental forces at microscopic scales. Quantum mechanics describes energy in discrete packets, or quanta, while general relativity treats gravity as a smooth curvature of spacetime. Reconciling these two descriptions is one of the central goals of quantum gravity. In the quantum realm, gravity is thought to emerge from hypothetical particles known as gravitons. These particles, if they exist, would mediate gravitational interactions much like photons mediate electromagnetism. Energy densities at quantum scales can become so extreme that they warp spacetime itself. This creates a feedback loop where energy influences gravity, and gravity in turn affects the distribution of energy. Virtual particles, constantly popping in and out of existence, contribute to energy fluctuations. These fluctuations may distort spacetime at quantum levels, adding to the complexity of describing gravity in this regime. Black holes provide a unique context for studying quantum energy and gravity. Near the event horizon, intense gravitational fields interact with quantum effects, producing phenomena like Hawking radiation. Hawking radiation demonstrates how energy and gravity intertwine at the quantum scale. It arises from particle-antiparticle pairs forming near the event horizon, with one particle escaping as radiation while the other falls into the black hole. The early universe offers another glimpse into this interplay. During the Planck era, energy densities were so high that quantum effects likely influenced the shape and behavior of spacetime itself. Understanding energy and gravity at these scales requires new mathematical tools. Current frameworks like string theory and loop quantum gravity attempt to describe how spacetime geometry responds to quantum energy distributions. The concept of zero-point energy, or the vacuum energy of quantum fields, further complicates the picture. This energy, predicted by quantum mechanics, has implications for the cosmological constant and the expansion of the universe. Experiments to detect gravitational effects at quantum scales remain challenging. However, advancements in precision measurements and high-energy physics may one day provide insights into this elusive interaction. Exploring the relationship between energy and gravity at the quantum level is essential for unifying our understanding of the universe. It offers the potential to uncover new principles governing the fundamental forces and the nature of spacetime. Dimensionality plays a fundamental role in shaping the physical laws that govern the universe. The number of dimensions determines how forces behave and how matter interacts within spacetime. In our everyday experience, we perceive three spatial dimensions and one of time, forming the familiar four-dimensional spacetime described by relativity. These dimensions define the framework in which objects move and interact. Gravity's strength diminishes with distance, a behavior tied directly to the number of spatial dimensions. If there were more or fewer dimensions, the force of gravity would behave very differently, altering the structure of the universe. Some theories, like string theory, propose the existence of additional spatial dimensions beyond the four we experience. These extra dimensions are thought to be compactified, curled up so tightly that they remain undetectable at ordinary scales. The presence of extra dimensions could influence fundamental forces, unifying them in a higher dimensional framework. This idea underpins attempts to reconcile gravity with quantum mechanics and the other forces. Extra dimensions might also provide explanations for phenomena we observe, such as the apparent weakness of gravity compared to other forces. Gravity could appear weak because it spreads across higher dimensions while other forces remain confined to the familiar four. In scenarios like black holes, dimensionality becomes crucial in determining their properties. A black hole in a universe with extra dimensions would behave differently, potentially revealing the presence of these hidden dimensions. The early universe may have experienced different effective dimensions as it expanded and cooled. At higher energies, the effects of extra dimensions might have been significant, shaping the evolution of spacetime. Dimensionality also impacts quantum gravity theories. In loop quantum gravity, spacetime is quantized into discrete chunks, while in string theory, particles are modeled as one-dimensional strings, vibrating in higher dimensional spaces. Holographic principles suggest that the information within a higher dimensional space can be encoded on a lower dimensional surface. This idea provides insights into black holes and the fundamental nature of spacetime. Experiments aimed at detecting the effects of extra dimensions include high-energy particle collisions and precise measurements of gravitational forces at small scales. Any deviations from expected behaviors could point to the existence of these hidden dimensions. Understanding the role of dimensionality goes beyond explaining what we observe. It may offer clues about the deeper structure of reality. The number and shape of dimensions influence everything from the forces of nature to the very existence of life in the universe. String theory offers a groundbreaking perspective by proposing that the fundamental building blocks of the universe are not particles, but tiny vibrating strings. These strings, much smaller than any particle we can currently observe, vibrate at different frequencies to give rise to various particles and forces. The theory unifies all particles and forces, including gravity, within a single framework. By describing particles as strings, it avoids the infinities that plague attempts to merge quantum mechanics with general relativity. String theory requires additional spatial dimensions for its mathematical consistency. In most formulations, the universe has 10 spatial dimensions, with 6 of them compactified into shapes too small to detect. These compactified dimensions influence how strings vibrate, determining the properties of particles. Different vibration patterns correspond to different masses, charges, and interactions, defining the diversity of particles in the universe. A key feature of string theory is supersymmetry, which pairs each particle with a heavier partner. Supersymmetry helps stabilize the theory and provides potential explanations for dark matter, though experimental evidence remains elusive. The theory also predicts the existence of gravitons, the quantum carriers of gravity. If observed, gravitons would validate string theory's approach to incorporating gravity into quantum mechanics. String interactions replace point-like collisions with smooth exchanges, reducing mathematical singularities. This smoothness helps address problems like the infinite curvature predicted at singularities in general relativity. The theory comes in multiple versions, but they are all connected by a higher dimensional framework known as M-theory. M-theory posits an 11-dimensional universe where strings coexist with higher dimensional objects called branes. These branes add depth to the theory, suggesting that our observable universe might be a 3-dimensional brane embedded in a higher dimensional space. This idea could explain why gravity behaves differently from other forces. String theory extends its reach to cosmology, offering explanations for the Big Bang and the early evolution of the universe. It suggests that interactions between branes could have triggered the birth of our cosmos. Despite its elegance, string theory faces challenges due to its lack of direct experimental evidence. The scales at which strings operate are far beyond the reach of current technology, making predictions difficult to test. Nonetheless, string theory remains a leading candidate for a unified theory of everything, providing a framework that bridges the quantum world with the cosmic scale of spacetime and gravity. Loop quantum gravity offers an alternative approach to unifying gravity with quantum mechanics, focusing on the structure of spacetime itself. Unlike string theory, it doesn't rely on additional dimensions or vibrating strings, but instead quantizes spacetime directly. At its core, loop quantum gravity proposes that spacetime is made up of discrete units like a woven fabric of loops. These loops are incredibly small at the Planck scale and form a dynamic network known as a spin network. Spin networks represent the quantum states of spacetime, where each loop or node corresponds to a quantized area or volume. This discretization eliminates the infinities that arise in classical general relativity. As spacetime evolves, these networks change, creating a process called spin foam. Spin foam provides a way to model spacetime as it transitions between quantum states, reflecting its dynamic and granular nature. The theory maintains the principles of general relativity but applies them at the quantum level. It preserves the geometric nature of gravity, describing it as the curvature of spacetime while incorporating quantum properties. Loop quantum gravity suggests that near singularities, such as those in black holes, spacetime's discrete structure prevents infinite densities. Instead, these regions may transition into entirely new states, avoiding the breakdown predicted by relativity. One of the key predictions of loop quantum gravity is the quantization of areas and volumes. These quantities take on specific values, much like energy levels in quantum mechanics, providing a clear distinction from the continuous model of classical spacetime. The theory also offers insights into the early universe, suggesting that the Big Bang could have been a big bounce. Instead of originating from a singularity, the universe may have expanded after collapsing from a prior state. Loop quantum gravity's emphasis on simplicity makes it appealing, as it doesn't require new particles or forces. Instead, it focuses on understanding the quantum nature of space-time using the existing framework of physics. While elegant, the theory faces challenges in making specific predictions. Its reliance on abstract mathematical models means that experimental verification remains elusive, though some phenomena, like quantum corrections to black hole behavior, could offer clues. Unlike string theory, which seeks a unifying framework for all forces, loop quantum gravity is more narrowly focused on quantizing gravity alone. This specialization allows it to address key issues in cosmology and black hole physics. Despite its limitations, loop quantum gravity provides a compelling vision of how spacetime might behave at the quantum level, challenging and expanding our understanding of the fundamental nature of reality. Causal dynamical triangulations offer a novel approach to understanding the quantum nature of spacetime. This framework attempts to build spacetime from simple geometric building blocks, emphasizing causality and structure. The core idea is to approximate spacetime by dividing it into tiny, discrete triangles or simplices. These simplices are then pieced together in a way that preserves the causal relationships between events, ensuring a coherent spacetime fabric. By assembling these building blocks, causal dynamical triangulations aim to construct a smooth spacetime at larger scales. The small-scale discreteness naturally transitions to the continuous spacetime we observe in the classical world. Causality plays a crucial role in this method, ensuring that the order of events remains consistent. This focus on causality distinguishes the approach from other quantum gravity theories and maintains alignment with relativity. The approach also incorporates time as a fundamental dimension, treating it differently from space. This separation helps avoid ambiguities that arise in other attempts to quantize space-time. Causal dynamical triangulations rely heavily on computational simulations to study the behavior of space-time. By running these simulations, researchers can observe how space-time emerges and evolves from the discrete simplices. One of the significant results of this approach is the emergence of a four-dimensional space-time at larger scales, matching our observed universe. This outcome provides strong evidence for the theory's validity. The theory also suggests that at the smallest scales, space-time has a fractal-like structure. This discovery indicates that space-time may be far more intricate and dynamic than previously imagined. By focusing on simple and well-defined rules, causal dynamical triangulations avoid some of the mathematical complexities of other quantum gravity theories. Its reliance on computation rather than purely abstract mathematics makes it a practical and testable framework. Despite its promise, the theory has limitations, particularly in connecting with experimental evidence. It remains challenging to identify observable phenomena that could confirm or refute its predictions. Causal dynamical triangulations also do not attempt to unify all forces, focusing instead on providing a quantum description of space-time. This narrower scope allows it to concentrate on resolving the core issues of quantum gravity. The method offers a unique perspective on how space-time might emerge from fundamental principles, bridging the gap between quantum mechanics and general relativity while opening new pathways for exploration. Asymptotic safety theory proposes that gravity can remain consistent and well-behaved at the smallest scales by introducing a fixed point in its behavior. This fixed point ensures that the strengths of gravitational interactions do not diverge, even at high energies. The concept of a fixed point means that certain quantities, like coupling constants, become stable and finite under extreme conditions. This stability prevents the infinities that typically arise when applying quantum mechanics to gravity. In this framework, spacetime remains continuous but behaves differently at various scales. At large scales, gravity behaves as described by general relativity, while at small scales, it adheres to the quantum corrections imposed by the fixed point. Asymptotic safety theory relies on renormalization group equations to track how physical constants evolve with changes in energy. These equations reveal whether gravity flows toward the fixed point as energy increases. A significant advantage of this approach is that it doesn't require additional dimensions or new particles. It works within the existing framework of quantum field theory, making it simpler to incorporate into current models. The theory provides potential explanations for the behavior of black holes, suggesting that quantum effects at the fixed point could regulate their interiors. This regulation might resolve singularities, replacing them with finite and well-defined structures. Asymptotic safety also offers insights into the early universe, where high-energy conditions prevailed. It suggests that space-time could have behaved differently near the Big Bang, governed by quantum fixed-point behavior. This approach has been explored in various contexts, including extensions to the standard model of particle physics. It could provide a unified framework for describing gravity alongside other fundamental forces. While promising, the theory faces challenges in making specific predictions that can be tested experimentally. The fixed point's existence is derived mathematically, but direct evidence remains elusive. Some researchers use computational methods to investigate the fixed point, simulating its effects on gravity. These efforts aim to connect theoretical predictions with observable phenomena. Asymptotic safety theory aligns with the broader search for quantum gravity by addressing infinities and maintaining consistency. Its simplicity and reliance on established principles make it an appealing candidate for further exploration. This theory continues to expand our understanding of gravity, offering a mathematically elegant solution to some of the most perplexing problems in modern physics. Beyond the major approaches, several alternative theories aim to address the challenge of quantum gravity. These theories explore diverse ideas, often challenging conventional assumptions about space-time and matter. One such approach is emergent gravity, which suggests that gravity isn't a fundamental force, but a byproduct of other physical processes. In this view, space-time and gravity emerge from more basic, underlying systems, like collective behaviors in condensed matter. Non-commutative geometry proposes that space-time coordinates are not continuous, but instead follow a quantized algebraic structure. This framework introduces a fundamentally different way of describing space-time at quantum scales. Twistor theory shifts the focus from space-time to light rays, representing physical processes using geometric objects called twistors. This theory provides an elegant mathematical framework that avoids many singularities. Another alternative is group field theory, which extends the ideas of loop quantum gravity by describing spacetime as a network of interacting quantum fields. It aims to unify the dynamics of quantum states with spacetime geometry. Causal sets offer a radically discrete view of spacetime, suggesting it is composed of fundamental building blocks arranged in a causal order. This theory eliminates the need for continuous spacetime, focusing entirely on the relationships between events. Horava-Lifshitz gravity modifies the behavior of spacetime at high energies, introducing anisotropy between space and time. This approach keeps spacetime continuous while altering its properties in the quantum regime. Quantum gravity envisions spacetime as an evolving network of relationships between points, where geometry arises dynamically. In this model, the universe's structure changes over time as connections form and break. Another proposal is entropic gravity, which treats gravity as an emergent phenomenon, driven by the thermodynamic behavior of information. This theory connects gravitational effects with entropy and information theory. Spin foam models build on the ideas of loop quantum gravity, describing spacetime as a sum over possible quantum states. These models visualize spacetime transitions as foam-like structures. The asymptotic quantization approach focuses on how spacetime behaves at infinity, offering new ways to reconcile quantum mechanics with gravitational waves and cosmic horizons. Some alternative theories incorporate ideas from condensed matter physics, treating spacetime as a quantum liquid or crystal. These analogies offer fresh perspectives on how spacetime might behave at small scales. Each of these theories contributes unique insights and challenges to the field of quantum gravity, broadening the scope of possibilities for understanding the universe's deepest mysteries. Dimensions in string theory are central to its framework, extending our understanding of the universe beyond the four familiar dimensions. In its most basic form, string theory requires 10 spacetime dimensions to remain mathematically consistent. Of these dimensions, 4 correspond to the ones we experience daily, 3 of space and 1 of time. The remaining 6 are compactified, curled up into shapes so small they evade direct observation. These extra dimensions are typically represented by intricate mathematical objects called Calabi-Yau manifolds. The specific geometry of these manifolds determines how strings vibrate, shaping the properties of particles and forces. The compactification of dimensions allows string theory to incorporate the observed universe while maintaining its mathematical structure. Without this compactification, the theory would produce results incompatible with what we observe. Each vibration mode of a string corresponds to a particle, and the extra dimensions influence these modes. This relationship ties the unseen dimensions directly to the physical properties of the universe, including mass and charge. The idea of extra dimensions also offers solutions to long-standing problems in physics, such as the hierarchy problem. By spreading gravity across additional dimensions, string theory explains why it appears weaker than other fundamental forces. In certain models, such as brane world scenarios, our universe exists as a three-dimensional brane within a higher dimensional space. While particles and forces are confined to the brane, gravity can extend into the extra dimensions. These additional dimensions might also play a role in unifying all fundamental forces. By incorporating them, string theory connects gravity, electromagnetism, and the nuclear forces within a single framework. Theoretical predictions suggest that at extremely high energies, like those found near the Big Bang, the effects of extra dimensions could have been significant. These dimensions might have influenced the evolution of the early universe. Experiments, such as those conducted at particle colliders, aim to detect signs of extra dimensions. Deviations in gravitational or particle behavior at small scales could point to their existence. While direct evidence of these dimensions remains elusive, their inclusion provides a deeper and more unified understanding of physical laws. The mathematical consistency they bring to string theory is a major reason for its continued development. The concept of extra dimensions challenges our perception of reality, offering a more intricate and expansive view of the universe. Their role in string theory underscores the potential for unseen layers of existence that shape the cosmos. In string theory, the fundamental components of the universe are not point-like particles, but tiny one-dimensional strings. These strings vibrate at different frequencies, and their oscillations determine the properties of particles, such as mass and charge. Unlike point particles, which exist at a single location, strings have spatial extent. This eliminates the infinite energy densities that arise in particle-based quantum theories, providing a smoother and more consistent description of interactions. Strings can vibrate in many different ways, with each mode of vibration corresponding to a specific particle. For example, one vibration might represent an electron, while another represents a photon or graviton. This versatility allows string theory to naturally include all known particles and forces, including gravity. The graviton, a hypothetical quantum carrier of gravity, arises as one of the vibration modes of a string. The extended nature of strings also modifies how interactions occur. Instead of point particles colliding, strings interact by merging and splitting, creating smoother transitions that avoid singularities. Strings can exist in different configurations, such as open strings with free ends or closed loops. Closed strings in particular are associated with gravity, while open strings often represent particles of other forces. Because strings replace point particles, they also redefine spacetime at the smallest scales. Their finite size introduces a natural limit to how small distances can be, avoiding the infinities seen in classical theories. The theory's reliance on strings instead of points helps unify quantum mechanics and general relativity. The smoothness of strings bridges the gap between the probabilistic quantum world and the geometric nature of spacetime. String theory also predicts higher dimensional objects known as branes, which arise from strings. These branes add complexity to the theory, suggesting that entire universes could exist as higher dimensional membranes. Replacing point particles with strings reduces mathematical inconsistencies, particularly in high-energy interactions. It creates a consistent framework where all forces and particles are connected. The extended nature of strings also helps explain the duality between particles and waves. A string's vibrations inherently combine these properties, aligning with the behavior observed in quantum mechanics. By replacing point particles with vibrating strings, the theory offers a richer and more flexible description of the universe, one that integrates all forces and particles into a single, unified framework. Supersymmetry is a theoretical framework that extends the standard model by pairing every particle with a corresponding superpartner. These superpartners differ in spin, but share similar properties, providing a deeper symmetry to the laws of physics. The introduction of supersymmetry helps address some key issues in particle physics, such as the hierarchy problem. By balancing interactions, it explains why the Higgs boson remains stable at high energies, avoiding the large corrections predicted without it. In supersymmetric models, particles like electrons and quarks have superpartners called selectrons and squarks, while bosons like photons have fermionic counterparts such as photinos. These additional particles double the particle spectrum, creating new possibilities for exploration. One of the most compelling implications of supersymmetry is its potential connection to dark matter. The lightest supersymmetric particle, often stable, is a strong candidate for the mysterious substance that makes up most of the universe's mass. Supersymmetry also plays a critical role in string theory, where it ensures mathematical consistency. The inclusion of superpartners allows string theory to remain free from anomalies, making it a viable model for unifying all forces. The framework suggests that supersymmetric particles existed in the early universe, influencing its evolution. These particles might have shaped the distribution of matter and energy during the first moments after the Big Bang. If supersymmetry exists, it could be tested at particle colliders, such as the Large Hadron Collider. Discovering superpartners would revolutionize our understanding of particle physics and confirm this elegant symmetry. However, the lack of direct evidence for supersymmetric particles at current energy levels raises questions about how it manifests in nature. Some theories propose that supersymmetry might be broken, with superpartners being heavier and harder to detect. Supersymmetry's implications extend beyond particle physics to quantum gravity. It provides a framework for incorporating gravity into a quantum description, a critical step toward a unified theory of everything. The balance it introduces also has implications for the cosmological constant, potentially solving issues related to the expansion of the universe. This could link supersymmetry to the behavior of dark energy. Theoretical predictions from supersymmetry, such as specific relationships between particle masses, guide experiments and help refine models. These tests ensure that the theory remains grounded in observable physics. Supersymmetry represents a powerful symmetry of nature, offering insights into unresolved mysteries and extending our understanding of the universe. Its discovery would mark a turning point in physics, revealing a deeper layer of reality. String theory faces significant challenges and criticisms, despite its potential as a unifying framework for physics. One major issue is the lack of direct experimental evidence, as the scales at which strings operate are far beyond current technological reach. The theory's reliance on extra dimensions, which are compactified and undetectable at ordinary scales, raises questions about its physical relevance. Without observable effects, these dimensions remain speculative. Another criticism is the sheer number of possible solutions in string theory. The landscape of vacua allows for an enormous variety of universes, making it difficult to identify which, if any, corresponds to our own. String theory's mathematical complexity is both a strength and a weakness. While it provides a rich framework, the equations are so intricate that making specific, testable predictions has proven elusive. The theory also struggles to fully incorporate dark matter and dark energy into its framework. While it offers potential explanations, it has yet to provide definitive answers for these dominant components of the universe. Some physicists argue that string theory is more of a mathematical construct than a physical theory. Its reliance on abstract concepts without experimental validation leads to skepticism about its role in describing reality. The energy scales needed to test string theory, such as those at the Planck scale, are far beyond the capabilities of current particle colliders. This limitation makes it unlikely that direct evidence for strings will be obtained in the near future. Another challenge is the dependence on supersymmetry, which has not yet been confirmed experimentally. Without evidence of superpartners, the foundation of string theory becomes less certain. String theory's inability to uniquely predict the constants of nature, such as particle masses and coupling strengths, is another point of contention. This makes it difficult to falsify or constrain the theory. Some alternative approaches to quantum gravity, like loop quantum gravity or causal dynamical triangulations, focus on directly quantizing spacetime without introducing strings or extra dimensions. These simpler models have drawn attention as potentially more testable alternatives. Critics also point out that string theory has not yet delivered on its original promise of unifying all forces and particles. While it provides a compelling framework, it has yet to resolve key issues in fundamental physics. Despite these criticisms, string theory remains a leading candidate for unifying quantum mechanics and gravity. Its challenges highlight the complexity of the problems it seeks to address and the ongoing need for creative solutions in theoretical physics. String theory's vast landscape of solutions naturally connects it to the multiverse hypothesis. With countless possible configurations of extra dimensions and physical constants, the theory suggests that our universe may be just one of many. Each unique configuration within the string theory landscape corresponds to a different universe, each with its own set of physical laws. These universes could vary dramatically, with some allowing life while others remain barren. The idea of a multiverse is tied to the concept of cosmic inflation, where rapid expansion in the early universe could have created separate regions, each with different physical properties. String theory provides a framework for understanding these variations. In some models, different regions of the multiverse are separated by vast distances, or even by additional dimensions. These universes might be inaccessible to one another, existing as isolated pockets of reality. The multiverse hypothesis offers potential explanations for the fine-tuning of physical constants in our universe. If countless universes exist, it's not surprising that at least one would have conditions suitable for life. String theory's reliance on extra dimensions aligns with the idea of a multiverse, as the geometry of these dimensions could vary across different universes. This variability adds richness to the multiverse concept. The theory also supports the notion of bubble universes, where different vacua form within a larger framework. Each bubble could represent a distinct universe with unique properties, arising from the string theory landscape. Critics argue that the multiverse hypothesis is inherently untestable, as other universes may lie beyond our observational reach. This raises philosophical questions about whether the hypothesis is scientific. Despite these challenges, the multiverse provides a way to address certain cosmological puzzles, like the apparent improbability of our universe's structure. String theory helps formalize these ideas within a mathematical context. Some interpretations suggest that black holes could act as gateways to other universes, linking the multiverse hypothesis to observable phenomena. However, this remains speculative and unproven. In the context of quantum mechanics, the multiverse aligns with the many worlds interpretation, where every quantum event spawns new branches of reality. String theory adds another layer to this interpretation through its vast landscape. By relating to the multiverse hypothesis, string theory expands the boundaries of what we consider possible, offering a framework to explore the deepest questions about the nature of reality and existence itself. Spacetime quantization suggests that spacetime, like energy, is not continuous but composed of discrete units. At the smallest scales, these units form a granular structure that fundamentally changes our understanding of geometry. This idea arises from attempts to unify general relativity and quantum mechanics. By quantizing spacetime, theories aim to resolve the infinities that appear when applying quantum principles to gravity. In loop quantum gravity, spacetime is quantized into tiny loops, creating a dynamic network of discrete chunks. These loops define the smallest possible areas and volumes, giving spacetime a finite structure. Quantization replaces the smooth curves of classical spacetime with a network of interconnected nodes. Each node represents a quantized piece of geometry, contributing to the overall structure of the universe. The concept also suggests a natural limit to how precisely distances and times can be measured. At scales near the Planck length, the granularity of spacetime imposes a fundamental uncertainty. Spacetime quantization provides an alternative to the singularities predicted by general relativity. In this framework, extreme conditions, such as those at black hole cores, are replaced by finite, well-defined structures. The idea is also key to understanding the early universe. During the Planck era, space-time quantization may have prevented infinite densities, offering a more coherent picture of the Big Bang. Spin networks and spin foams are mathematical tools used to describe quantized spacetime. These models show how spacetime evolves over time, transitioning between quantum states. Quantization could explain why spacetime behaves differently at large and small scales. It offers a way to bridge the smoothness of classical relativity with the probabilistic nature of quantum mechanics. Experimental verification of spacetime quantization remains challenging, as its effects are only apparent at incredibly small scales. However, indirect evidence, such as deviations in gravitational waves or high-energy particle behavior, could offer clues. Some theories suggest that spacetime quantization might leave imprints in the cosmic microwave background, providing a potential observational link. These imprints could reveal the granularity of spacetime in the universe's earliest moments. Spacetime quantization reshapes our understanding of reality, replacing the continuous fabric of classical physics with a dynamic, discrete structure. It provides a foundation for resolving the deepest conflicts between quantum mechanics and general relativity. Spin networks and spin foams are mathematical tools used to describe the quantum geometry of spacetime in loop quantum gravity. They provide a way to visualize how spacetime is constructed from discrete units. A spin network represents a static configuration of spacetime, where nodes and links correspond to quantized areas and volumes. These networks form the building blocks of the universe at the smallest scales. The nodes in a spin network are points where quantum states of spacetime meet, and the links between them represent relationships or interactions. Together, they create a web-like structure that defines the geometry. Spin networks are not fixed but evolve over time, reflecting the dynamic nature of spacetime. This evolution is described by spin foams, which extend the idea into the time dimension. A spin foam is a higher dimensional structure that represents spacetime transitions between different quantum states. It is essentially a collection of spin networks evolving and interacting over time. These foams visualize spacetime as a process, where individual quantum events connect to form the larger structure of the universe. Each transition captures how geometry changes in the quantum realm. Spin networks and spin foams provide a discrete and finite description of spacetime, avoiding the infinities that arise in classical general relativity. They offer a framework where spacetime is both quantized and dynamic. The approach also predicts specific areas and volumes for spacetime regions, quantized like energy levels in quantum mechanics. This discrete nature provides a new way to understand black hole entropy and horizons. Spin foams incorporate the probabilistic aspects of quantum mechanics, describing spacetime as a sum over all possible transitions. This aligns the framework with the principles of quantum theory. These models are particularly useful in understanding extreme conditions, like the interior of black holes or the universe's earliest moments. They replace singularities with finite, well-defined quantum structures. Experimental evidence for spin networks and spin foams is still being explored. Observations of gravitational waves, black hole behavior, or cosmic background radiation may provide indirect support for their predictions. Spin networks and spin foams offer a glimpse into the quantum fabric of spacetime, bridging the gap between general relativity and quantum mechanics with an innovative and mathematically elegant approach. Loop quantum gravity makes several intriguing predictions about the quantum nature of spacetime and its effects on the universe. One of its most notable claims is that spacetime is fundamentally discrete, made up of quantized areas and volumes. This discreteness implies a natural cutoff to the smallest possible scales, eliminating the infinities that arise in classical physics. It suggests that lengths, areas, and volumes exist in discrete steps rather than being continuous. Near black holes, loop quantum gravity predicts that the singularities described by general relativity do not exist. Instead, spacetime forms a finite and structured core, preventing the infinite densities that classical physics suggests. The theory also offers an explanation for black hole entropy, tying it to the quantized geometry of the event horizon. Each quantum unit of spacetime contributes to the entropy, providing a deeper understanding of black hole thermodynamics. In the context of the Big Bang, loop quantum gravity predicts a big bounce rather than a singularity. It suggests that the universe's contraction prior to the Big Bang transitions smoothly into the current expansion, avoiding an infinite collapse. Another prediction involves the behavior of gravitational waves. Loop quantum gravity suggests that their propagation might reveal traces of spacetime's quantum structure, offering potential observational evidence. Cosmic background radiation could carry imprints of the universe's quantum geometry. These subtle patterns in the radiation might reflect the discrete nature of spacetime during the universe's early moments. The theory also predicts that quantum corrections to classical spacetime might become significant in extreme conditions. This could lead to measurable deviations from general relativity near black holes or in highly energetic cosmic events. Loop quantum gravity provides a framework for understanding the origin of time. It proposes that time emerges from the evolution of quantum states, offering a new perspective on the nature of temporal flow. These predictions align with the idea that spacetime is not a fixed backdrop, but a dynamic and quantized entity. As a result, loop quantum gravity reshapes how we view the fundamental structure of the universe. While direct evidence for these predictions remains elusive, indirect tests through cosmology, gravitational wave data, and black hole studies could provide critical insights. Observing deviations from classical models would support the theory's claims. Loop quantum gravity's predictions challenge and expand the boundaries of modern physics, offering a fresh lens through which to explore the deepest mysteries of the cosmos. Loop quantum gravity and string theory offer contrasting approaches to the problem of quantum gravity. While both seek to unify quantum mechanics and general relativity, their methods and assumptions differ fundamentally. String theory posits that the basic building blocks of the universe are tiny, vibrating strings, while loop quantum gravity focuses on quantizing spacetime itself into discrete units. This distinction shapes the scope and goals of each theory. String theory requires extra dimensions to function mathematically, envisioning a universe with up to 10 or 11 dimensions. In contrast, loop quantum gravity operates within the four-dimensional spacetime we experience, avoiding the need for additional dimensions. The two theories also differ in their treatment of matter and forces. String theory aims to unify all fundamental forces and particles, including gravity, in a single framework. Loop quantum gravity, however, focuses specifically on the quantum aspects of spacetime and does not inherently address other forces. String theory relies heavily on supersymmetry, pairing each particle with a superpartner. This assumption, while elegant, remains unconfirmed experimentally. Loop quantum gravity avoids such assumptions, grounding itself in existing physical principles. In terms of mathematical complexity, string theory is often regarded as more intricate, involving higher dimensional geometries and abstract constructs. Loop quantum gravity's models, such as spin networks and spin foams, are comparatively simpler and more closely tied to spacetime geometry. Theories also differ in their experimental prospects. String theory predicts phenomena at scales far beyond current technology, making direct tests challenging. Loop quantum gravity, on the other hand, offers predictions like quantum corrections to black holes or gravitational waves, which may be observable with advanced techniques. String theory's multiverse hypothesis stems from its vast landscape of solutions, suggesting countless possible universes. Loop quantum gravity, focused on quantizing spacetime, does not inherently lead to a multiverse, narrowing its scope to our observable universe. Both theories aim to address singularities, but they approach the problem differently. String theory replaces singularities with smooth structures through string interactions, while loop quantum gravity suggests that spacetime's discreteness prevents their formation. The philosophies behind the theories also diverge. String theory seeks a unified framework for all of physics, embracing ambitious assumptions about the universe's structure. Loop quantum gravity adopts a more conservative stance, addressing gravity specifically with minimal extensions to known physics. While string theory often captivates with its elegance and breadth, loop quantum gravity offers practical and testable insights into the quantum nature of spacetime. Each theory contributes unique perspectives to the quest for understanding the universe. Ultimately, string theory and loop quantum gravity represent complementary approaches. Together, they expand the possibilities for solving the profound mysteries of quantum gravity and the nature of spacetime. Experimental possibilities for studying quantum gravity remain limited, but emerging technologies and creative approaches offer hope for testing key predictions. These experiments aim to bridge the gap between theoretical models and observable phenomena. Gravitational wave detectors, such as LIGO and Virgo, provide a unique opportunity to explore quantum gravity effects. Subtle deviations in the behavior of gravitational waves could hint at the quantum structure of spacetime. Observations of black holes are another promising avenue. High-resolution imaging of black hole event horizons and the behavior of matter near them may reveal quantum corrections predicted by theories like loop quantum gravity. The study of cosmic microwave background radiation offers clues about the universe's earliest moments. Tiny fluctuations in this relic radiation could carry imprints of quantum spacetime from the Planck era. Particle accelerators like the Large Hadron Collider explore energy scales approaching those needed for quantum gravity effects. While direct evidence of strings or gravitons remains out of reach, unexpected anomalies could offer indirect insights. Quantum experiments on Earth also hold potential. Precision tests of gravity at small scales may uncover deviations from classical predictions, suggesting the influence of quantum effects. The search for dark matter and dark energy could intersect with quantum gravity research. If these phenomena have quantum origins, their detection might provide indirect support for specific theories. Cosmic rays and high-energy astrophysical events offer natural laboratories for quantum gravity. Particles traveling across vast cosmic distances could experience effects from the discrete structure of spacetime, leaving measurable traces. Tabletop experiments are exploring the quantum behavior of macroscopic systems. Tests involving tiny suspended mirrors or entangled particles under gravitational influence aim to probe the intersection of quantum mechanics and gravity. Advancements in quantum technology, such as atomic clocks and interferometers, are pushing the boundaries of precision measurement. These tools could detect subtle effects predicted by quantum gravity, like time dilation at quantum scales. Satellite-based experiments extend these possibilities further. Missions designed to study gravitational anomalies or test equivalence principles might uncover hints of quantum space-time behavior. While direct detection of quantum gravity remains a distant goal, the convergence of astrophysics, particle physics, and quantum technology continues to open new pathways. These experimental efforts bring us closer to uncovering the quantum nature of the universe. Black hole singularities represent regions where gravity becomes so intense that space-time is infinitely curved. At these points, the known laws of physics break down, leaving many questions unanswered. General relativity predicts these singularities at the centers of black holes, where all the matter that falls in is compressed to a single point. However, quantum mechanics suggests that such infinities cannot exist, pointing to a deeper, unresolved theory. The event horizon, the boundary of a black hole, prevents anything from escaping once it crosses. This includes light and information, making the interior of a black hole effectively hidden from the outside universe. One of the most intriguing puzzles is the black hole information paradox. When a black hole evaporates through Hawking radiation, it appears that the information about what fell into the black hole is lost forever. This apparent loss of information contradicts the principles of quantum mechanics, which state that information must be preserved. Resolving this paradox is a central challenge in quantum gravity. Hawking radiation is caused by quantum effects near the event horizon, where particle-antiparticle pairs form. One particle escapes as radiation, while the other falls into the black hole, slowly causing it to evaporate. The evaporation of black holes raises the question of what happens to the information about the particles that created them. If information is truly lost, it undermines the foundations of quantum theory. Some theories propose that information is encoded in the Hawking radiation itself, though this would require mechanisms for its retrieval that remain speculative. Others suggest that information is preserved on the event horizon in a holographic form. The idea of the holographic principle ties into this, proposing that all the information about a black hole's interior is encoded on its two-dimensional surface. This principle could provide a pathway to resolving the paradox. Loop quantum gravity suggests that singularities are replaced by finite structured cores, preventing the infinite collapse predicted by relativity. In this framework, information may be stored in the quantum structure of spacetime. String theory offers another perspective, proposing that black holes are made up of strings or brains, which could store and preserve information. These structures avoid singularities by spreading mass and energy over finite dimensions. The resolution of the information paradox could reshape our understanding of both quantum mechanics and general relativity. Black holes continue to serve as a unique testing ground for the deepest mysteries of the universe. Hawking radiation arises from quantum effects near the event horizon of a black hole. It occurs when particle-antiparticle pairs form due to fluctuations in spacetime, with one escaping and the other falling into the black hole. This radiation causes black holes to lose mass over time, leading to their gradual evaporation. Eventually, a black hole could shrink to nothing, leaving behind a profound question about what happens to the information it contained. Hawking radiation combines principles from both quantum mechanics and general relativity, making it a key phenomenon in the study of quantum gravity. It reveals that black holes are not completely black, but emit thermal radiation. The temperature of Hawking radiation is inversely proportional to the black hole's mass. Smaller black holes emit more radiation, evaporating faster than their larger counterparts. The process challenges the traditional view of black holes as regions where nothing can escape. It suggests that black holes are dynamic systems, slowly radiating energy back into the universe. Hawking radiation also ties into the black hole information paradox. If the radiation contains no information about what fell into the black hole, it implies a loss of information that contradicts quantum mechanics. Some theories propose that information is encoded within the radiation, though this remains difficult to prove. If true, it would require a mechanism to transfer information from the black hole's interior to the escaping radiation. The holographic principle offers one possible solution. It suggests that all information about the black hole's interior is stored on its surface, and this information might be imprinted on the Hawking radiation. Quantum effects near the event horizon also suggest that spacetime behaves differently at these boundaries. These effects may provide insights into how gravity and quantum mechanics interact at the smallest scales. Hawking radiation has not yet been observed directly, as it is incredibly faint and challenging to detect. However, researchers are exploring analog systems, like black hole analogs in fluid dynamics, to study its properties. The study of Hawking radiation provides a unique opportunity to test theories of quantum gravity. It bridges the gap between quantum mechanics and general relativity, offering clues about the nature of spacetime. This phenomenon continues to inspire new ideas about the relationship between information, matter, and the quantum fabric of the universe, making it a cornerstone in the search for a unified theory of physics. Black holes serve as natural laboratories for testing the interplay between quantum mechanics and general relativity. Their extreme environments push the boundaries of our understanding, making them ideal for exploring quantum gravity. The intense gravitational fields near a black hole's event horizon create conditions where spacetime is heavily warped. These regions reveal how gravity behaves under extreme conditions, offering insights that cannot be replicated on Earth. Hawking radiation, predicted to emerge from black holes, directly links quantum effects to gravitational phenomena. Observing this radiation, even indirectly, could provide crucial evidence for theories uniting quantum mechanics and gravity. The study of black hole mergers through gravitational wave observations has opened a new window into their dynamics. These events reveal how spacetime ripples and interacts under the most violent cosmic conditions. Black hole information paradox challenges, such as the fate of information when a black hole evaporates, make them pivotal in questioning the fundamental principles of quantum mechanics. Solving this paradox could reshape physics itself. High-energy particle interactions near black holes mimic conditions from the early universe, allowing researchers to test predictions about spacetime's quantum structure. These interactions could reveal traces of quantum corrections to general relativity. The interiors of black holes, while hidden by the event horizon, remain a focus for theoretical research. Models like loop quantum gravity suggest that singularities may be replaced by finite structured cores, offering testable predictions. Black holes may also be connected to the holographic principle, which posits that all information about their interior is encoded on their two-dimensional surface. This principle provides a potential link between gravity, quantum mechanics, and information theory. Observing the behavior of matter and light as they approach a black hole's event horizon offers real-world data. These observations help refine models of spacetime curvature and quantum effects. Future technologies, such as advanced telescopes and interferometers, promise to capture even more detailed data about black holes. This could include detecting subtle deviations from classical predictions caused by quantum phenomena. Analog black holes created in laboratories allow researchers to simulate aspects of black hole behavior. These analogs provide valuable insights into phenomena like Hawking radiation and quantum tunneling. As testing grounds, black holes remain at the frontier of theoretical and observational physics. They challenge existing paradigms and offer a pathway toward understanding the quantum nature of spacetime. Holography provides a profound connection between quantum gravity and the nature of spacetime. It suggests that information in a higher dimensional space can be fully described by a lower dimensional boundary. The holographic principle is rooted in studies of black hole thermodynamics. It proposes that all the information contained within a black hole is encoded on its event horizon, a two-dimensional surface. This concept extends beyond black holes to the universe itself. It implies that our three-dimensional world could be a holographic projection of information stored on a two-dimensional boundary. ADS-CFT correspondence is a specific realization of holography, linking a gravitational theory in a higher dimensional space to a quantum field theory on its lower dimensional boundary. This duality provides a mathematical bridge between gravity and quantum mechanics. Holography resolves certain paradoxes, like the black hole information problem, by ensuring that information is never truly lost. Instead, it is preserved on the surface, consistent with the principles of quantum mechanics. The principle offers a new way to think about spacetime, where geometry and gravity emerge from quantum information stored on a boundary. This perspective transforms how we understand the fabric of the universe. Connections to holography have inspired models of quantum gravity that prioritize information and entropy. These models suggest that space-time itself could be a manifestation of underlying quantum states. Holography also provides tools for studying strongly coupled quantum systems. By mapping complex quantum interactions to gravitational analogues, it simplifies calculations and reveals new insights. In cosmology, holography has implications for the early universe. It suggests that the Big Bang may have originated from a two-dimensional boundary, with our three-dimensional world emerging over time. Experiments like studying gravitational waves or high-energy cosmic phenomena may offer indirect evidence for holography. Patterns in these data could reflect the influence of lower-dimensional information. Holography bridges fundamental physics with areas like quantum computing and information theory. Its emphasis on encoding and retrieving information connects it to broader questions about reality and the universe's structure. As a framework, holography has the potential to unify disparate areas of physics. It provides a fresh perspective on quantum gravity, black holes, and the very origins of spacetime itself. The quantum nature of gravity has profound implications for the structure of the universe. It suggests that spacetime is not a smooth continuum, but a dynamic and discrete fabric at its smallest scales. If spacetime is quantized, then its geometry may influence the formation of cosmic structures. The granularity of spacetime could leave imprints on the distribution of galaxies and clusters in the universe. The early universe would have been shaped by quantum fluctuations in spacetime. These fluctuations may have seeded the large-scale structures we observe today, such as galaxies and cosmic filaments. Black holes provide another insight into the universe's structure. Their quantum properties, including holographic encoding of information, hint at a deeper connection between gravity and the organization of matter. The holographic principle implies that the universe itself might be a lower-dimensional projection of quantum information. This concept challenges our classical understanding of space and time, offering a radical new perspective. Dark energy, driving the accelerated expansion of the universe, could be linked to quantum gravity effects. The energy of the vacuum, influenced by quantum fields, may play a role in shaping space-time's large-scale behavior. Quantum corrections to general relativity might also explain anomalies in the behavior of galaxies and galaxy clusters. These corrections could offer alternatives to theories like dark matter or modifications of gravity. If extra dimensions exist as proposed in string theory, they would directly influence the universe's structure. These dimensions could alter the behavior of gravitational forces, changing the way matter clumps and forms. Cosmic inflation, a rapid expansion in the early universe, may have connections to quantum gravity. Quantum effects during this phase could have determined the uniformity and small perturbations we see in the cosmic microwave background. The universe's ultimate fate is another area impacted by quantum gravity. Whether it ends in a big crunch, expands forever, or transitions to another phase might depend on how space-time behaves at quantum scales. The relationship between time and space also shifts under quantum gravity. If time emerges from quantum processes, it changes how we view the evolution and history of the universe as a whole. These implications reshape our understanding of the cosmos, connecting its large-scale structure to the smallest quantum interactions. They suggest a universe that is deeply interconnected, governed by principles that transcend classical physics. Holography in physics is the idea that the information within a volume of space can be represented entirely on its boundary. This principle challenges traditional views of space and dimensionality, offering a revolutionary way to understand the universe. The concept originated from studies of black holes, where it was discovered that the entropy of a black hole is proportional to the area of its event horizon, not its volume. This suggested that all the information about what falls into a black hole is encoded on its surface. Holography extends this idea to the entire universe, proposing that our three-dimensional world could be a projection of quantum information stored on a two-dimensional boundary. This radical notion reshapes how we think about reality. ADS-CFT correspondence is a key example of holography, linking a gravitational theory in a higher dimensional space to a quantum field theory on its lower dimensional boundary. This duality provides a concrete mathematical framework for holographic ideas. In this context, gravity and spacetime geometry emerge from the quantum properties of the boundary theory. This connection unifies concepts from quantum mechanics, relativity, and field theory in a single framework. Holography offers solutions to paradoxes like black hole information loss. By encoding information on a surface, it ensures that quantum mechanics remains consistent, preserving the principle that information cannot be destroyed. This principle also redefines the relationship between volume and surface area in physics. It suggests that the fundamental degrees of freedom in a region are determined by its boundary, not its interior. Holography has practical applications beyond theoretical physics. It provides tools for studying strongly coupled quantum systems, using gravitational analogues to simplify complex problems in condensed matter physics. In cosmology, holography implies that the early universe could have originated from information encoded on a lower dimensional surface. This perspective offers new insights into the origins and evolution of spacetime. Holographic ideas connect deeply with the concept of entropy, tying the structure of spacetime to the flow of information. This link provides a framework for understanding phenomena like black hole thermodynamics. The concept also bridges physics with information theory, emphasizing the role of quantum information in shaping reality. It highlights how encoding, storage, and retrieval of information are fundamental to the universe's structure. Holography represents a shift in our understanding of dimensions and reality, revealing that the fabric of the universe may be more deeply connected to information than to the physical structures we observe. ADS-CFT correspondence is a specific realization of the holographic principle, providing a bridge between gravity and quantum field theory. It establishes a duality between a gravitational theory in an anti-de Sitter or ADS space and a conformal field theory or CFT on its boundary. In this framework, the dynamics of gravity in a higher dimensional ADS space are fully equivalent to the behavior of a quantum field theory in one fewer dimension. This relationship connects the geometric properties of spacetime with the quantum properties of particles and fields. ADS-CFT correspondence is often referred to as a holographic duality because it encapsulates how a higher dimensional space can be encoded on a lower dimensional boundary. This duality provides a mathematical foundation for exploring quantum gravity. The ADS space itself has a negative curvature, creating a specific kind of geometry where distances stretch exponentially. This setting allows the duality to work mathematically, though it doesn't directly describe our universe, which has a positive curvature due to dark energy. The conformal field theory, on the other hand, operates without gravity and focuses on symmetries and interactions between particles. Its simpler structure makes it easier to study, while still encoding the complexities of the gravitational system. ADS-CFT is a powerful tool for understanding black holes. It suggests that all the information within a black hole, including its quantum properties, is encoded on the ADS boundary, offering a resolution to the information paradox. This correspondence has implications beyond gravity. It is used to study strongly interacting quantum systems in condensed matter physics, where it simplifies calculations that would otherwise be intractable. The duality also provides insights into the behavior of quantum chromodynamics, or QCD, the theory of the strong nuclear force. ADS-CFT offers approximations that help describe how quarks and gluons interact under extreme conditions. ADS-CFT has been instrumental in advancing our understanding of string theory, as it emerges naturally from string models in higher dimensions. The correspondence ties together ideas from strings, gravity, and field theory into a cohesive framework. While AD-CFT is not directly applicable to our universe's de Sitter geometry, researchers are exploring extensions of the correspondence that could work in more realistic cosmological settings. This remains an active area of study. The correspondence highlights the deep connections between quantum mechanics and space-time geometry, revealing how gravitational phenomena emerge from quantum principles. It offers a new way to explore the universe's fundamental structure. AD-CFT continues to inspire research in theoretical physics, acting as a bridge between different areas of science. It exemplifies how dualities can simplify complex problems and reveal hidden symmetries in the laws of nature. The implications of quantum gravity extend deeply into our understanding of spacetime and gravity. At the smallest scales, spacetime may no longer be a smooth continuum, but a dynamic quantized structure. This quantization implies that spacetime is made up of discrete units, challenging classical assumptions of infinite divisibility. Such granularity could fundamentally alter how distances, areas, and volumes are defined. Gravity, traditionally described as the curvature of spacetime in general relativity, gains new meaning in a quantum framework. It may emerge from underlying quantum processes, linking spacetime geometry directly to quantum states. In a holographic perspective, gravity is seen as an emergent phenomenon arising from lower dimensional information. This idea suggests that the force of gravity is a consequence of quantum interactions encoded on spacetime's boundaries. Quantum corrections to gravity could become significant near black holes or the Big Bang, replacing singularities with finite, structured cores. These corrections provide a way to avoid infinities and explain extreme cosmic events. Spacetime's dynamic nature also means that it is not a fixed backdrop for events, but an active participant in the universe's evolution. Quantum fluctuations in spacetime could influence everything from particle interactions to cosmic expansion. The relationship between time and space shifts under quantum gravity. If time itself emerges from quantum processes, it raises questions about causality and the nature of temporal flow at fundamental levels. Quantum gravity impacts our understanding of horizons, such as those around black holes. These boundaries, once thought to obscure information, may encode all the quantum details of the regions they enclose. The discreteness of spacetime might leave detectable signatures in phenomena like gravitational waves or the cosmic microwave background. Observing these effects could provide direct evidence of quantum gravity's influence. The interplay between gravity and quantum mechanics also suggests new mechanisms for energy transfer and particle interactions. These mechanisms might bridge the gap between macroscopic forces and microscopic phenomena. Understanding quantum gravity reshapes cosmology, offering explanations for the universe's large-scale structure and its origins. It connects the early moments of the universe to quantum processes that continue to influence it today. Ultimately, quantum gravity provides a deeper framework for spacetime and gravity, unifying them with quantum mechanics. It reveals a universe that is intricately interconnected, governed by principles far beyond classical understanding. Experimental verification of quantum gravity is one of the most challenging goals in modern physics. The scales at which quantum gravity effects become significant are far beyond current technological capabilities. Gravitational wave observatories like LIGO and Virgo offer indirect opportunities to detect quantum gravity signatures. Subtle deviations in the patterns of these waves could hint at the quantum structure of spacetime. Astrophysical observations, particularly of black holes and neutron stars, provide another avenue. Studying the behavior of matter and radiation near these extreme objects may reveal effects predicted by quantum gravity. The cosmic microwave background is a key target for detecting early universe quantum effects. Fluctuations in this relic radiation could carry imprints of quantum spacetime from the Planck era. Particle colliders like the Large Hadron Collider explore energy scales approaching those where quantum gravity may manifest. While direct detection of gravitons or strings is unlikely, unexpected anomalies could offer indirect evidence. High-energy cosmic rays that travel vast distances across the universe might interact with quantum spacetime. These interactions could lead to observable deviations in their paths or energy distributions. Precision tests of gravity at small scales are another promising approach. Experiments measuring gravitational forces at micron distances could uncover deviations from classical predictions. Analog black hole experiments conducted in laboratories simulate aspects of black hole physics. These models allow researchers to explore phenomena like Hawking radiation in controlled settings. Quantum optics and interferometry are advancing the search for quantum gravity. These techniques measure minute changes in space-time geometry, potentially revealing quantum corrections. Satellites designed to test the equivalence principle or study gravitational anomalies might detect small-scale effects linked to quantum gravity. These missions extend experimental efforts beyond Earth's surface. Emerging technologies in quantum computing and ultra-cold matter offer innovative ways to probe the quantum aspects of gravity. These systems provide unprecedented precision in measuring fundamental interactions. Although direct verification remains elusive, these diverse experimental efforts bring us closer to understanding quantum gravity. They combine creative approaches with cutting-edge technology to explore the universe's most fundamental principles. Holography provides a profound connection between space-time, information, and entropy. It suggests that the entropy of a system is fundamentally tied to its boundary rather than its volume. This idea first emerged from black hole thermodynamics, where the entropy of a black hole was found to be proportional to the area of its event horizon. This discovery challenges classical expectations, linking entropy to surface geometry. The holographic principle extends this insight, proposing that all the information within a region of space can be encoded on its boundary. This principle ties the structure of space-time to the fundamental limits of information storage. Entropy, in this context, measures the number of microscopic configurations that a system can have. For a black hole, these configurations correspond to quantum states of space-time encoded on the horizon. The relationship between holography and entropy suggests that space-time itself may emerge from the flow and organization of information. This concept redefines gravity and geometry as emergent phenomena. In cosmology, holography implies that the entropy of the universe could be encoded on its cosmic horizon. This idea offers a new way to think about the large-scale structure and evolution of the cosmos. Holography also influences our understanding of quantum field theory. It links the entropy of quantum systems to their holographic duals, providing insights into strongly coupled systems. The ADAS-CFT correspondence highlights this connection, where the entropy of a gravitational system in anti-de Sitter space corresponds to the entropy of its boundary conformal field theory. This duality simplifies complex calculations in physics. Holography challenges traditional views of locality, suggesting that information can be stored non-locally on a system's boundary. This non-locality reshapes our understanding of space-time and interactions. Entropy plays a central role in the black hole information paradox. The holographic perspective ensures that information is preserved, resolving the apparent loss of entropy during black hole evaporation. The concept also ties deeply into quantum computing and information theory, where entropy measures the limits of processing and storing information. Holography bridges these ideas with fundamental physics. By connecting entropy to boundaries and information, holography reveals a universe deeply rooted in the principles of organization and storage. It offers a unifying framework that links gravity, thermodynamics, and quantum theory. Current limitations in experimentation make testing quantum gravity a significant challenge. The energy scales required to directly observe quantum gravity effects are far beyond the reach of current technology. The Planck scale, where quantum gravity phenomena are expected to dominate, is around 10 to the 19 giga-electronvolts. Achieving these energies would require particle accelerators millions of times more powerful than those available today. Black holes, key testing grounds for quantum gravity, are distant and difficult to study directly. While gravitational wave observations provide some insights, the extreme conditions within black holes remain inaccessible. Hawking radiation, a critical prediction linking quantum mechanics and gravity, is too faint to detect with current instruments. Its detection would require advanced technology capable of observing minuscule temperature variations near black holes. The compactification of extra dimensions proposed by string theory makes them challenging to observe. These dimensions are thought to be incredibly small, beyond the precision of even the most sensitive experiments. Cosmic observations, such as those of the cosmic microwave background, are limited by the resolution and sensitivity of current telescopes. Subtle quantum signatures in this radiation may remain hidden until technology improves. Precision tests of gravity at small scales, such as in tabletop experiments, face practical barriers like isolating systems from external disturbances. Achieving the necessary sensitivity is an ongoing technical challenge. The theoretical predictions of many quantum gravity models like string theory or loop quantum gravity often lack specific testable consequences. This makes it difficult to design experiments that can falsify or validate these theories. Quantum experiments attempting to probe the interplay of gravity and quantum mechanics are limited by their scale. Bridging the macroscopic effects of gravity with the microscopic realm of quantum systems remains elusive. Cosmic rays and high-energy particles, while promising, are subject to interference and noise as they travel through space. Extracting meaningful data about quantum spacetime from these signals is a complex task. Laboratory analogues of black holes and other quantum gravity phenomena are limited in their ability to replicate the extreme conditions of the universe. While insightful, these analogues may not capture all relevant aspects of quantum gravity. Despite these limitations, advancements in technology and creative experimental designs continue to push the boundaries. Progress in this field requires both theoretical innovation and the development of next-generation instruments. Gravitational wave observations have opened a new window into the universe, providing a way to study extreme events like black hole mergers and neutron star collisions. These ripples in spacetime, predicted by Einstein's theory of general relativity, carry information about their origins and the structure of spacetime itself. Detectors like LIGO and Virgo have successfully captured these waves, confirming the existence of black holes and the dynamics of their interactions. Each detection offers a unique opportunity to explore the universe's most violent and energetic processes. Gravitational waves travel vast distances without significant distortion, making them a pristine source of information about distant cosmic events. Their properties could reveal quantum corrections to spacetime at high energy scales. The merging of black holes produces waves with unique patterns or waveforms that reflect their masses, spins, and orbits. Analyzing these waveforms allows researchers to test the limits of general relativity and search for deviations predicted by quantum gravity. Neutron star mergers provide another key source of gravitational waves. These events also produce electromagnetic signals, offering a multi-messenger approach to studying the universe and the role of gravity. Quantum gravity theories suggest that gravitational waves could exhibit small deviations from classical predictions. Detecting such anomalies would provide direct evidence for the quantum nature of spacetime. Gravitational wave data might also reveal properties of black hole horizons, such as quantum effects predicted by the holographic principle. These observations could help resolve the black hole information paradox. By studying waves from different cosmic epochs, researchers can probe the evolution of spacetime over billions of years. Early universe signals, though difficult to detect, might carry imprints of quantum spacetime from the Big Bang. The precision of gravitational wave detectors continues to improve, expanding their sensitivity to smaller and more subtle signals. Future observatories like the Einstein telescope and LISA will extend these capabilities, exploring new frequency ranges. These advancements could allow the detection of primordial gravitational waves, which are thought to originate from quantum fluctuations during cosmic inflation. Such observations would provide a direct link between quantum mechanics and gravity. Gravitational wave observations are also providing insights into dark matter and dark energy. If quantum gravity affects these mysterious components, its influence could manifest in wave patterns or propagation. This field represents a growing frontier in physics, combining theoretical predictions with cutting-edge technology. Gravitational waves offer a unique perspective on the universe, bridging the classical and quantum realms. Particle accelerators play a vital role in probing the fundamental forces of nature and exploring energy scales relevant to quantum gravity. By smashing particles together at near-light speeds, they recreate extreme conditions similar to those of the early universe. The Large Hadron Collider is currently the most powerful accelerator, exploring energy levels where new particles and interactions might emerge. While still far below the Planck scale, it provides critical data on the behavior of matter and forces. Accelerators test predictions from quantum gravity theories, such as the existence of extra dimensions. If extra dimensions influence particle interactions, their effects might appear as subtle deviations in collision outcomes. The search for microscopic black holes at colliders is another area of interest. Some theories suggest that high-energy collisions could briefly create these tiny black holes, offering direct evidence of quantum gravity. Particle accelerators also investigate supersymmetry, a cornerstone of string theory. Discovering superpartners would validate key aspects of this framework and strengthen its connection to quantum gravity. Precision measurements of particle masses and interactions provide clues about unifying gravity with other forces. Anomalies in these measurements could hint at quantum gravity effects influencing the standard model. Future accelerators aim to reach even higher energies, narrowing the gap toward scales where quantum gravity becomes dominant. These next-generation machines will push the boundaries of particle physics. Accelerators also contribute to our understanding of dark matter. If dark matter particles interact weakly with known forces, their traces might be detected in high-energy collisions, offering indirect insights into quantum gravity. The behavior of quantum fields under extreme conditions, such as those created in heavy ion collisions, reveals new properties of matter and spacetime. These experiments mimic the high-energy environments where quantum gravity effects may appear. By producing and studying exotic particles, accelerators test the limits of quantum mechanics. Understanding how particles interact at high energies helps refine theories attempting to unify quantum mechanics and gravity. Accelerators serve as testing grounds for theories predicting new phenomena, such as string resonances or gravitons. Observing these effects would revolutionize our understanding of space-time. While current accelerators cannot directly reach the Planck scale, their discoveries inform the development of quantum gravity models. They remain essential tools for advancing both theoretical and experimental physics. The cosmic microwave background, or CMB, is a relic of the early universe, carrying imprints of its structure just 380,000 years after the Big Bang. Studying the CMB provides a unique window into the conditions and processes that shape the cosmos. Subtle fluctuations in the CMB temperature and polarization reflect the distribution of matter and energy in the early universe. These patterns offer critical data for testing theories of cosmic inflation and quantum gravity. Quantum fluctuations during the inflationary period are believed to have seeded the structures we observe today, such as galaxies and galaxy clusters. The CMB encodes these quantum imprints, preserving them across billions of years. The search for primordial gravitational waves in the CMB is a key focus. These waves, generated by quantum processes during inflation, could reveal the quantum nature of spacetime at the smallest scales. B modes, a specific polarization pattern in the CMB, are considered a smoking gun for detecting gravitational waves. Observing these patterns would confirm the quantum origin of large-scale structures in the universe. High-precision measurements of the CMB spectrum also test the standard cosmological model. Deviations from predicted values could indicate new physics, including the effects of quantum gravity. The CMB provides constraints on dark energy and dark matter, both of which influence the universe's evolution. Understanding how these components interact with spacetime could reveal deeper connections to quantum gravity. Advanced telescopes and satellite missions, such as Planck and the upcoming CMB-S4 experiment, continue to refine our understanding of the CMB. These projects aim to detect even fainter signals, pushing the boundaries of sensitivity. The interplay between quantum fields and spacetime during the early universe is encoded in the CMB. Extracting this information could bridge the gap between quantum mechanics and general relativity. Holographic theories suggest that the CMB might contain information about higher dimensional processes. Studying its intricate patterns could provide indirect evidence for these radical ideas. The anisotropies in the CMB also help test models of quantum corrections to gravity. Small-scale irregularities might reflect quantum effects that classical physics cannot explain. Cosmic microwave background studies continue to be a cornerstone of cosmology. By decoding its signals, researchers hope to uncover the quantum origins of the universe and the nature of spacetime itself. Detecting quantum gravity effects remains one of the most difficult tasks in modern physics. The primary challenge is that these effects occur at incredibly small scales, near the Planck length, far beyond the reach of current experimental technology. The energies required to probe quantum gravity directly are orders of magnitude higher than those produced by particle accelerators. Achieving such conditions would demand technological advances that are still far in the future. Another challenge is the subtlety of quantum gravity effects. Even if they occur at larger scales, their influence may be minuscule, easily masked by noise or classical gravitational phenomena. Theoretical predictions from quantum gravity models often lack precision. Without clear, testable outcomes, designing experiments to detect these effects becomes an enormous challenge. Cosmic observations, such as those of gravitational waves or the cosmic microwave background, offer indirect methods for studying quantum gravity. However, separating quantum signals from classical or astrophysical noise is a significant obstacle. The compactified dimensions proposed by string theory remain undetectable with current instrumentation. These extra dimensions, if they exist, are too small to influence measurements at observable scales. Testing holographic principles or the discreteness of spacetime requires unprecedented precision. Small deviations in particle behavior or gravitational forces could hold clues, but isolating these effects is extremely difficult. Laboratory analogues, such as black hole analog systems, attempt to replicate quantum gravity phenomena. While useful, these models can only approximate the complex conditions of the actual universe. Quantum gravity effects might also depend on unknown factors, such as the specific nature of spacetime at high energies. Without a clear understanding, researchers face challenges in identifying where and how to look for these effects. Astrophysical events like black hole mergers offer unique opportunities, but their signals are often faint and require extensive data analysis. Detecting quantum corrections in such events remains a major hurdle. The interaction of quantum gravity with other forces like electromagnetism or the strong force could produce observable effects. However, disentangling these interactions from standard physics requires highly sensitive measurements. Despite these challenges, progress in technology and theoretical refinement continues to push the boundaries. Overcoming these obstacles will require innovative approaches and interdisciplinary collaboration across physics, cosmology, and quantum technology. Interpretations of quantum gravity aim to reconcile the fundamental principles of quantum mechanics with the geometric nature of general relativity. These interpretations provide different perspectives on how spacetime and matter interact at the smallest scales. One interpretation suggests that gravity is not a fundamental force, but an emergent phenomenon arising from the collective behavior of quantum systems. This view reimagines spacetime as a product of quantum interactions rather than a pre-existing framework. Another perspective comes from loop quantum gravity, which proposes that spacetime is quantized into discrete units. This interpretation focuses on the granular structure of spacetime, replacing the smooth continuum of classical physics. String theory offers a different view, interpreting particles and forces as manifestations of tiny vibrating strings. These strings unify all interactions under a single theoretical framework, including gravity. Holographic interpretations suggest that the universe's three-dimensional structure is encoded on a two-dimensional surface. This perspective redefines spacetime and gravity as emergent properties of underlying quantum information. Some interpretations focus on the role of information, viewing spacetime as a dynamic network that encodes relationships between events. This approach ties gravity to the flow and transformation of information at quantum scales. In causal set theory, spacetime is composed of discrete points linked by causal relationships. This interpretation emphasizes the sequential nature of events, building spacetime from a fundamental order. Thermodynamic interpretations connect gravity to entropy and the flow of heat. In this view, spacetime geometry arises from the statistical behavior of quantum systems, linking gravity to the laws of thermodynamics. Non-commutative geometry offers a mathematical interpretation where spacetime coordinates follow quantum algebra rules. This framework suggests that spacetime itself behaves like a quantum entity, subject to uncertainty. Asymptotic safety theory interprets gravity through the lens of renormalization, proposing that gravitational interactions stabilize at high energies. This interpretation avoids infinities and preserves the predictability of quantum gravity. Multiverse interpretations, often tied to string theory, suggest that quantum gravity phenomena give rise to multiple universes with distinct physical laws. This view extends the scope of quantum gravity beyond a single cosmos. Each interpretation highlights a unique aspect of quantum gravity, offering different tools and insights. Together, They expand our understanding and guide the search for a unified description of the universe. Quantum gravity profoundly impacts our understanding of reality, challenging long-held assumptions about space, time, and existence. It suggests that the fabric of the universe is not continuous, but composed of discrete units. This idea transforms spacetime from a passive stage into a dynamic entity that interacts with matter and energy. It redefines the universe as a system where geometry and quantum mechanics are deeply intertwined. The emergence of spacetime from quantum processes implies that time itself is not fundamental. Instead, it may arise from the evolution of quantum states, altering our perception of causality and the flow of events. Quantum gravity highlights the interconnectedness of all things, showing that particles, forces, and spacetime are part of a unified quantum framework. This challenges the classical separation of matter and geometry. The concept of a holographic universe suggests that the reality we experience is a projection of quantum information. This perspective questions the nature of dimensionality and the fundamental structure of existence. By eliminating singularities, quantum gravity reshapes our understanding of cosmic phenomena like black holes and the Big Bang. It replaces infinite densities with finite, comprehensible structures. The theory's implications extend to the origins of the universe, where quantum fluctuations may have determined the large-scale structure of the cosmos. This connects the quantum realm to the vastness of space. Quantum gravity also forces us to reconsider locality, suggesting that events separated by vast distances may still be fundamentally connected. This challenges traditional views of cause and effect. The unification of quantum mechanics and gravity reveals a universe governed by principles far beyond classical physics. It invites new interpretations of reality, from the behavior of particles to the nature of time. This deeper understanding of spacetime influences fields like information theory, where the role of entropy and encoding becomes central to describing the universe. It connects physics with concepts of computation and data. Quantum gravity's impact on reality extends to philosophy, raising questions about the observer's role in shaping the universe. It suggests that reality is not absolute, but shaped by quantum interactions and observations. Ultimately, quantum gravity reveals a universe that is more interconnected, dynamic, and complex than previously imagined. It offers a framework that unites the smallest particles with the grandest structures, reshaping our fundamental view of existence. Time at the quantum level takes on a fundamentally different nature from the classical understanding. Rather than being a continuous flow, time may emerge from the underlying dynamics of quantum systems. Quantum gravity suggests that time is not an absolute background but a relational property, defined through the interactions of particles and fields. This challenges the traditional notion of a universal clock. Causality, too, becomes less rigid at quantum scales. In quantum mechanics, events can exhibit non-local correlations, as seen in entanglement, where particles influence one another instantly across vast distances. In theories like loop quantum gravity, time is woven into the quantized structure of spacetime. It emerges as a parameter describing the evolution of discrete spacetime elements rather than a continuous dimension. Holographic principles introduce the idea that time and causality may be encoded on a lower dimensional boundary. This perspective reframes the flow of time as an emergent property of quantum information processes. The uncertainty principle complicates causality by imposing limits on how precisely time and energy can be measured. This introduces an inherent fuzziness to the sequencing of quantum events. In the quantum realm, processes do not follow fixed timelines, but exist as probabilities until observed. This probabilistic nature forces us to rethink the linear progression of cause and effect. Quantum experiments, such as delayed choice setups, demonstrate that decisions made in the present can seemingly influence the outcomes of past events. These effects challenge classical interpretations of time's arrow. The interplay between time and gravity becomes even more complex in extreme conditions like black holes. Near the event horizon, time slows relative to distant observers, blending the concepts of space and time. In some interpretations, time might not exist as a fundamental concept at all. Instead, it could be a convenient abstraction, arising from the entanglement and interactions of quantum states. Causality at the quantum level does not always align with classical expectations. Events that appear to be causally disconnected may share underlying quantum links, reshaping how we think about influence and order. These insights reveal time and causality as emergent phenomena tied to the quantum structure of reality. They challenge classical physics and open new pathways for understanding the universe's deepest workings. Mathematics serves as the foundation for understanding quantum gravity, providing the language to describe spacetime, particles, and forces at their most fundamental levels. Its precision allows for the exploration of concepts far beyond direct observation. Abstract mathematical structures, such as tensors, manifolds, and operators, form the core tools for describing spacetime geometry and quantum fields. These tools enable physicists to model the universe in ways that classical methods cannot. The equations of general relativity and quantum mechanics, though distinct, both rely heavily on mathematical abstraction. Quantum gravity attempts to unify these frameworks, requiring new mathematical innovations. Techniques like topology and group theory are used to explore the properties of spacetime, especially in models like loop quantum gravity and string theory. These fields help define how spacetime behaves at the smallest scales. String theory in particular leverages higher dimensional mathematics to describe the vibrations of strings and the geometry of extra dimensions. This level of abstraction is necessary to unify gravity with other fundamental forces. In loop quantum gravity, spin networks and spin foams are mathematically modeled to represent the quantized nature of spacetime. These abstract structures offer a new perspective on geometry and its role in the universe. ADS-CFT correspondence, a cornerstone of holography, is built on advanced mathematical dualities. It connects gravitational theories in higher dimensional spaces to quantum field theories on lower dimensional boundaries, showcasing the power of abstraction. Mathematical consistency often drives theoretical progress, even when experimental validation is lacking. For quantum gravity, ensuring that models remain mathematically sound is crucial for their potential to describe reality. Abstraction also allows for the development of computational methods, enabling simulations of phenomena like black hole mergers or quantum corrections to gravity. These simulations provide valuable insights into complex interactions. While mathematics abstracts away from physical intuition, it also guides discoveries. Patterns, symmetries, and invariants found in equations often reveal deeper truths about the universe's structure. The reliance on mathematics underscores the importance of interdisciplinary approaches, where physicists, mathematicians, and computational scientists collaborate to refine theories and solve complex problems. Mathematical abstraction not only expands the scope of what can be understood, but also unifies seemingly disparate areas of physics, creating a coherent framework for exploring the fundamental nature of reality. The pursuit of advanced knowledge in quantum gravity and the fundamental nature of the universe carries profound ethical implications. As our understanding deepens, the potential for transformative technologies emerges, requiring careful consideration of their societal impact. Quantum gravity research could lead to breakthroughs in energy, computation, and space exploration. These advancements hold the promise of immense benefits, but also the risk of exacerbating inequality if access is not equitable. Theoretical discoveries often influence practical applications in unforeseen ways. Understanding the fabric of space-time might lead to technologies that challenge existing norms, reshaping economics, governance, and daily life. Advanced knowledge raises questions about responsibility in its use. Scientists, policymakers, and the public must navigate how to balance innovation with the potential for misuse or unintended consequences. Holography and quantum information theories, for example, might revolutionize communication and security systems. While these advancements enhance capabilities, they also introduce ethical concerns about privacy and surveillance. The pursuit of knowledge itself must consider the allocation of resources. Large-scale projects like particle accelerators or space-based observatories require significant investment, prompting discussions about their societal priorities. Public engagement becomes crucial as knowledge advances. Complex theories often feel inaccessible, yet their implications affect everyone. Transparent communication is essential to building trust and fostering informed decision-making. As we push the boundaries of understanding, there is a risk of hubris in assuming total mastery over nature. Quantum gravity challenges fundamental concepts, reminding us of the limits of human knowledge and the need for humility. The exploration of the universe's origins and structure intersects with philosophical and existential questions. What responsibilities come with uncovering truths about existence, and how do they shape humanity's role in the cosmos? The global nature of science demands international cooperation. Advanced knowledge must transcend political and cultural divisions, promoting unity in addressing universal challenges and opportunities. Ethical frameworks need to evolve alongside scientific progress. These frameworks should integrate insights from diverse disciplines, including philosophy, sociology, and cultural studies, ensuring holistic approaches to innovation. Ultimately, the ethical implications of advanced knowledge call for a shared commitment to using discoveries for the collective good. Balancing curiosity with caution ensures that the pursuit of quantum gravity enriches humanity without compromising its future. Current breakthroughs in quantum gravity research are advancing our understanding of the universe at both theoretical and experimental levels. These achievements highlight the growing synergy between cutting-edge technology and innovative ideas. The detection of gravitational waves by LIGO and Virgo has been a transformative milestone. These observations confirm predictions of general relativity and open new avenues to explore quantum corrections to spacetime. High-resolution images of black holes, like those produced by the Event Horizon Telescope, offer unprecedented data on extreme gravitational environments. These images provide indirect insights into the quantum behavior of space-time near event horizons. Advances in quantum computing are beginning to influence quantum gravity research. Simulating complex systems, such as black hole entropy or holographic principles, is becoming more feasible with quantum algorithms. Projects like the Large Hadron Collider continue to push the boundaries of high-energy physics. While direct evidence for quantum gravity remains elusive, the search for new particles and forces informs theoretical models. Upcoming gravitational wave observatories, such as LISA and the Einstein Telescope, promise to detect subtler signals, including potential signatures of quantum spacetime. These projects aim to extend our observational reach into previously unexplored frequencies. The James Webb Space Telescope is providing deeper insights into the early universe. Its observations may uncover clues about the interplay between quantum processes and cosmic evolution during the first billion years. In cosmology, studies of the cosmic microwave background are refining our understanding of quantum fluctuations during inflation. New experiments aim to detect primordial gravitational waves, linking the quantum realm to the universe's largest scales. Holographic principles are being tested through laboratory analogues, where researchers simulate aspects of black hole physics. These experiments explore the relationship between entropy, information, and space-time. Efforts to unify string theory and loop quantum gravity are producing hybrid models that integrate the strengths of both approaches. These collaborations highlight the importance of cross-disciplinary perspectives in addressing quantum gravity. Dark matter detection projects such as Xenon and Lux Zeppelin are advancing rapidly. If dark matter has quantum origins, its discovery could provide direct evidence of quantum gravity effects on particle behavior. International collaborations, including CERN and space-based observatories, emphasize the global nature of quantum gravity research. These partnerships combine resources and expertise, accelerating progress in understanding the universe's fundamental laws. Breakthroughs and projects in quantum gravity represent the culmination of decades of effort. Each discovery brings us closer to a unified framework, revealing the quantum structure of space-time and its role in shaping the cosmos. Interdisciplinary collaborations are essential for advancing quantum gravity research, bringing together diverse fields to address its complex challenges. These partnerships bridge gaps between theory, experiment, and computation. Physicists and mathematicians work closely to refine the mathematical frameworks underlying quantum gravity. Advanced tools like topology and algebraic geometry are crucial for modeling quantum spacetime. Collaboration with cosmologists provides insights into the universe's early moments. Observations of the cosmic microwave background and large-scale structures inform theories about quantum fluctuations and spacetime dynamics. Astrophysicists contribute through studies of black holes, neutron stars, and gravitational waves. These extreme environments test the limits of general relativity and reveal potential quantum corrections to gravity. Particle physicists play a vital role in exploring high-energy phenomena. Experiments at colliders and detectors probe for evidence of new particles and forces predicted by quantum gravity models. Quantum computing experts are developing algorithms to simulate complex quantum systems. These simulations are essential for testing ideas like holography and understanding quantum spacetime behavior. Engineers and technologists provide the tools and instruments needed for precision measurements. Advances in detector sensitivity, satellite technology, and quantum sensors expand the range of observable phenomena. Philosophers and ethicists engage with the implications of quantum gravity. They explore questions about time, causality, and the nature of reality, as well as the societal impact of groundbreaking discoveries. Computer scientists contribute through machine learning and data analysis, enabling the interpretation of vast datasets from gravitational wave observatories and cosmological surveys. Collaborations with material scientists and chemists help design advanced materials for detectors and quantum experiments. These materials improve sensitivity and enable experiments at previously inaccessible scales. International organizations like CERN and space agencies foster global partnerships. They coordinate resources and expertise across nations, ensuring that quantum gravity research benefits from a unified effort. Interdisciplinary approaches unlock new possibilities by combining perspectives and methods from multiple fields. They ensure that quantum gravity research progresses in a holistic, innovative, and collaborative manner. Artificial intelligence and advanced computation are transforming the study of quantum gravity, enabling researchers to tackle problems that were previously intractable. These tools provide new ways to explore complex theories and analyze massive datasets. Machine learning algorithms are being applied to analyze gravitational wave signals, identifying patterns and anomalies that might indicate quantum effects in space-time. These techniques can process data far faster than traditional methods. AI is also enhancing simulations of black hole mergers and other astrophysical phenomena. By modeling these events with greater accuracy, researchers gain insights into quantum corrections to general relativity. Quantum computers are emerging as powerful tools for simulating quantum gravity scenarios. They can process the intricate interactions of quantum fields and space-time geometry with unprecedented efficiency. In holography research, computational models are used to test the ADS-CFT correspondence. AI helps identify correlations between gravitational theories and their quantum field theory duals, refining our understanding of this duality. Neural networks are being trained to explore the structure of extra dimensions in string theory. These models can identify patterns in the compactification of dimensions that would be difficult to discern manually. AI-driven optimization techniques are used to design experiments from particle collisions to tabletop tests of gravity. These methods ensure that resources are allocated efficiently and experimental setups are fine-tuned for maximum sensitivity. Computation plays a critical role in analyzing data from cosmological surveys and the cosmic microwave background. Advanced algorithms extract subtle signals that could reveal quantum fluctuations in the early universe. In loop quantum gravity, AI aids in visualizing spin networks and spin foams. These visualizations help researchers interpret the quantized structure of spacetime and its dynamic evolution. Artificial intelligence also facilitates interdisciplinary collaboration. By integrating data from astrophysics, particle physics, and cosmology, it bridges gaps between fields and uncovers new connections. Data-driven approaches supported by AI are transforming theoretical physics, allowing researchers to test predictions against empirical observations with greater precision. These methods accelerate the validation of quantum gravity theories. As computation continues to evolve, its role in quantum gravity research will only grow. Artificial intelligence and advanced modeling are essential for navigating the complexities of spacetime and uncovering the quantum foundations of the universe. Quantum gravity research holds the potential to revolutionize technology in ways we are only beginning to imagine. By deepening our understanding of spacetime and quantum processes, it opens doors to groundbreaking innovations. One potential application is in quantum computing. Insights from quantum gravity could enhance algorithms and materials, pushing the boundaries of computational power and solving problems previously thought unsolvable. The study of spacetime geometry may lead to advances in navigation and timing systems. Precision improvements in technologies like GPS could result from a better understanding of gravity at quantum scales. Energy technologies could benefit from quantum gravity by revealing new ways to manipulate space-time and energy fields. This might pave the way for breakthroughs in energy storage and transfer systems. Advances in quantum information theory inspired by holography could enhance data encryption and secure communication. These methods would redefine security protocols, making them nearly impervious to conventional hacking. In medicine, quantum gravity's principles could inspire innovative imaging technologies. The ability to detect minute changes in spacetime might translate into ultra-sensitive diagnostic tools. Exploration of the quantum structure of spacetime could influence material science, leading to the development of stronger, lighter, and more versatile materials. These materials could have applications across industries, from aerospace to construction. Space exploration could see significant benefits. Understanding gravity at quantum levels might enable new propulsion methods, or even the manipulation of space-time for interstellar travel. Gravitational wave technologies derived from quantum gravity studies might evolve into tools for monitoring environmental changes or detecting subterranean structures, offering applications in geology and disaster prevention. Quantum gravity research could lead to new paradigms in energy generation, possibly even harnessing quantum fluctuations in vacuum energy for practical use. This could radically transform the energy sector. Technologies derived from black hole studies might influence data storage, creating systems with unprecedented capacity and efficiency. Insights from entropy and holography could revolutionize how information is encoded and retrieved. These potential applications reflect just a fraction of what quantum gravity research could offer. As understanding deepens, the technologies inspired by these discoveries may reshape industries, societies, and the way we live. The quest for unification represents one of the most profound challenges in science, aiming to bridge the gap between quantum mechanics and general relativity. It seeks a single framework to describe the universe's fundamental forces and structures. This journey reflects humanity's enduring curiosity about the cosmos, pushing the boundaries of knowledge to uncover the hidden principles governing reality. It's a quest that combines theoretical brilliance with experimental ingenuity. Unifying these theories is about more than equations. It's about understanding the fabric of existence. It connects the smallest particles with the grandest structures, revealing the deep unity of nature. The path to unification has reshaped physics, leading to breakthroughs like quantum field theory, the Standard Model, and discoveries in cosmology. Each step forward offers new tools and perspectives. Theories like string theory and loop quantum gravity provide glimpses of this unified framework, each offering unique insights. These approaches highlight the creativity and diversity of thought driving this quest. Unification also challenges our philosophical understanding of reality. It forces us to reconsider concepts like time, space, causality, and the nature of existence itself. The search brings humanity together through collaboration, crossing borders and disciplines. It's a shared endeavor, uniting physicists, mathematicians, and visionaries around a common goal. While experimental verification remains challenging, each observation of black holes, gravitational waves, and the early universe brings us closer. The cosmos itself becomes the ultimate laboratory for testing these ideas. The quest for unification is not just about solving equations, but also about inspiring generations. It symbolizes the human spirit's drive to explore, understand, and create. This pursuit may redefine technology, society, and even how we view our place in the universe. Its implications stretch far beyond physics, touching every aspect of our lives. At its core, unification is about connecting the fragmented pieces of understanding into a cohesive whole. It reminds us that the universe is an intricate tapestry, woven from the threads of mathematics, science, and imagination. The journey may be long, but every step reveals new wonders. The quest for unification is a testament to our capacity for discovery, reminding us that the universe's mysteries are as vast as our curiosity. Today we've taken an incredible journey through the intricate world of quantum gravity, exploring its theories, implications, and groundbreaking possibilities. We started by unraveling the fundamental conflict between general relativity and quantum mechanics, two pillars of modern physics that describe reality in seemingly incompatible ways. We delved into key concepts like spacetime curvature, quantum states, and the role of uncertainty. These ideas form the backbone of quantum gravity, challenging our classical understanding of the universe and inspiring new frameworks to unify these theories. The video explored cutting-edge approaches, from string theory with its elegant vibrating strings and extra dimensions, to loop quantum gravity and its quantized space-time networks. Each offers a unique perspective on how to resolve the mysteries of gravity at quantum scales. We examined the role of black holes as natural laboratories for quantum gravity, particularly their singularities and the information paradox. These enigmatic objects continue to be at the center of efforts to understand the quantum fabric of spacetime. Gravitational wave observations and cosmic microwave background studies revealed how experimental physics intersects with theoretical breakthroughs. These tools are helping scientists inch closer to verifying the predictions of quantum gravity theories. Holography and AD-CFT correspondence demonstrated how quantum gravity might connect with quantum field theory, offering an elegant duality that reshapes our understanding of dimensions and reality. We also looked at the role of artificial intelligence and computation in advancing research. From simulating black hole mergers to analyzing massive datasets, these technologies are accelerating the quest for unification. The potential applications of quantum gravity stretch beyond theoretical physics, offering transformative possibilities in technology, medicine, and space exploration. These advancements could reshape industries and redefine what's possible. This journey highlighted the collaborative nature of quantum gravity research, bringing together physicists, mathematicians, and technologists. The interdisciplinary approach underscores the universal pursuit of understanding the cosmos. If you enjoyed this deep dive into quantum gravity, don't forget to like the video and subscribe to the channel. Your support helps us continue creating content that explores the mysteries of science and the universe. Be sure to check out our other videos covering topics from black holes to quantum mechanics. Together, let's keep exploring the wonders of the cosmos.